Right now, at this very moment, something is screaming at the bottom of the ocean. Not a figure of speech, not a metaphor, not some poetic embellishment designed to set a mood. Something, somewhere beneath miles of salt water, in pressures that would collapse a nuclear submarine, and in darkness so total that the human eye becomes useless within seconds, is producing a sound so loud that it can be detected on instruments stationed thousands of miles away. And after decades of recording, decades of analysis, and decades of some of the most sophisticated acoustic science ever conducted, no one can say with complete certainty what is making that sound. The ocean covers more than 70% of the surface of this planet. It fills basins that reach depths of nearly 11 kilometers. It holds an estimated 1.335 billion cubic kilometers of water, and within that incomprehensible volume, there are sounds. Not the sounds you might expect, the gentle lapping of waves against a hull, the distant song of a humpback whale. Those sounds exist, of course, but they are the surface of the story. Beneath them, in the deep places where light has never reached and where no human eye has ever looked without the aid of a machine, there are other sounds entirely. Sounds that do not belong to any catalogued species. Sounds that do not match any known geological process. Sounds so powerful that they register on military-grade listening arrays originally built to track enemy submarines during the Cold War. Sounds that sweep upward through frequencies, pulse in rhythmic patterns for hours before vanishing without warning, or shake the ocean floor with a low, grinding roar that seems to belong to something impossibly, almost absurdly large. These sounds have been recorded. They have been given names: the bloop, the upsweep, the slowdown, Julia, the train, the whistle. Each one is a discrete acoustic event, captured on spectrograms, analyzed by experts, debated at conferences, and published in peer-reviewed journals. And yet many of them remain, in the strictest possible scientific sense, unexplained. The bloop has been tentatively attributed to Antarctic ice. The upsweep has been provisionally linked to underwater volcanic activity. The slowdown has been connected to the grinding of glacial ice against the seafloor. But in case after case, the attribution is tentative, the evidence circumstantial, the definitive proof absent. The deep ocean keeps making sounds, and we keep failing, or at least struggling, to explain them. In 1997, a listening station operated by the National Oceanic and Atmospheric Administration, known as NOAA, detected one of the loudest underwater sounds ever recorded. It was detected on hydrophones separated by more than 5,000 kilometers. It rose in frequency over roughly 1 minute. It was so powerful that early estimates suggested it was louder than the call of a blue whale, the largest and loudest animal on the planet. The researchers named it the Bloop, and for years it was the most famous mystery in ocean science. But the Bloop was not alone. It was one entry in a growing catalogue of unknown signals, a catalogue that expands every year as new recordings accumulate faster than they can be analysed. Consider the scale of what we do not know. Fewer human beings have been to the deepest point in the ocean than have walked on the surface of the moon. We have mapped more of the surface of Mars than we have mapped of our own ocean floor. The deep ocean, the abyssal and hadal zones below 4,000 meters, represents the single largest living space on this planet, and we have explored, by most estimates, roughly 5% of the world's oceans. 95% remains essentially unvisited, uncharted, unknown. And from that unknown darkness, sounds continue to rise, captured by instruments we barely have the resources to maintain, recorded in archives we barely have the time to review. By the end of tonight, you're going to understand not just what these sounds are, but what they represent. You are going to understand the physics of sound in water, how it travels faster and farther than sound in air, how the ocean contains a hidden channel that acts like a fiber optic cable for acoustic energy, bending and guiding sounds across entire hemispheres with almost no loss of power. You are going to understand the biology of creatures that live in permanent darkness, under pressures that would crush steel, creatures that communicate and navigate and hunt using sound because there is no other way. You are going to understand the geology of a planet that groans and shifts beneath miles of water, producing acoustic signals that travel the length of ocean basins. And you are going to understand The philosophical weight of all of this, the weight of knowing that the largest environment on the planet we call home is one we have barely begun to explore, and that its sounds, rising through the water column day and night, year after year, represent a language we have only just begun to hear. Before we get started, if you find these mysteries as fascinating as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. There is something deeply unsettling about a sound that has no source, or rather, a sound whose source we cannot identify, despite our best efforts. We are not a species accustomed to ignorance. We have named millions of organisms. We have charted the orbits of distant worlds. We have decoded the structure of the molecule that carries our genetic information. And yet, beneath the surface of the water that covers most of our own planet, there are noises that we have recorded, analysed, and still cannot explain. That gap, between hearing and understanding, between detecting and identifying, is the space this story occupies. The recordings exist, the spectrograms are published, the names have been assigned, but the questions remain open. What is calling from the deepest places on Earth? What produces frequencies that travel through 5,000 kilometers of black, freezing water? What is the abyss trying to tell us? If only we knew how to listen. Now, let's begin. To understand the sounds that rise from the abyss, we first have to understand the abyss itself. Not as a metaphor, not as a vague notion of deep water, but as a physical space with real dimensions, real pressures, and real conditions that dictate what can live there, what can travel through it, and what can be heard within its boundaries. The average depth of the world's oceans is approximately 3,800 meters. That is nearly 4 kilometers of water, measured from the surface downward, sitting above the seafloor in a typical stretch of open ocean. To a person standing on a beach, 4 kilometers sounds like a manageable distance. It is the length of a moderate walk, the kind of thing you could complete in 45 minutes at a comfortable pace. But 4 kilometers of water is not the same as 4 kilometers of land. Water is dense, water is heavy, water presses down on everything beneath it with a force that increases relentlessly with depth, and 4 kilometers of it, stacked in a vertical column above the ocean floor, creates conditions that are fundamentally hostile to almost everything designed to exist at the surface. The deepest point in the ocean is Challenger Deep, a narrow slot at the southern end of the Mariana Trench in the western Pacific Ocean, east of the Mariana Islands. Challenger Deep reaches a maximum known depth of approximately 10,994 meters. That is nearly 11 kilometers beneath the surface. To grasp what this means, consider the tallest structure on dry land. Mount Everest, the highest point on the surface of the Earth, rises to an altitude of 8,849 meters above sea level. If you could somehow lift Mount Everest from its base in the Himalayas and place it at the bottom of the Mariana Trench, its summit would be submerged under more than 2,000 meters of water. There would be more than 2 kilometers of ocean above the peak of the tallest mountain on the planet. The ocean, at its deepest, is deeper than the land is tall. The vertical scale of this planet is dominated not by what rises above the surface, but by what sinks beneath it. That comparison deserves a moment of stillness. Every mountaineer who has stood on the summit of Everest did so at a height of roughly 8.85 kilometers above sea level. Every explorer who has descended to Challenger Deep did so at a depth of roughly 11 kilometers below the surface. The distance from the peak of Everest to the bottom of the Mariana Trench spans nearly 20 kilometers of vertical space, and the ocean claims the larger share. But depth in the ocean is not simply distance, it is pressure. For every 10 meters of seawater above you, the pressure increases by approximately 1 atmosphere. 1 atmosphere is the pressure exerted by the weight of the air at sea level, roughly 14.7 pounds per square inch. At 10 meters below the surface, you are under 2 atmospheres. At 100 meters, roughly 11 atmospheres. At 1,000 meters, approximately 101 atmospheres. At 3,800 meters, the average depth of the ocean, the pressure is approximately 381 atmospheres. And at the bottom of the Mariana Trench, roughly 10,994 meters down, the pressure reaches approximately 1,086 atmospheres. 1,086 atmospheres. That number is abstract until you translate it into physical force. It is equivalent to roughly 16,000 pounds pressing on every single square inch of surface. Imagine placing 50 large commercial aircraft on top of a single postage stamp. That is the crushing weight of water at the bottom of the deepest trench on Earth. It would collapse a conventional submarine like a tin can. It would compress the gases in a human lung to a volume so small that they would cease to function. It would squeeze any air-filled cavity flat. Consider a styrofoam cup, the kind used for coffee. If you attached such a cup to the outside of a deep-sea submersible and sent it to the bottom of the Mariana Trench, it would come back compressed to the size of a thimble, its molecular structure crushed by the weight of the water above. This is not a thought experiment. Researchers have done this. The compressed cups sit in laboratories and museums as quiet reminders of what 11 kilometers of water can do. The pressure at these depths also changes the behavior of familiar substances in ways that challenge intuition. Gases dissolve more readily into liquids under pressure. Chemical reactions proceed at different rates. The density of the water itself increases, though only slightly, under the immense weight of the column above. Even sound, which we will return to shortly, behaves differently. Its speed changes with pressure, with temperature, and with the salinity of the water, and these changes have profound consequences for how acoustic signals propagate through the deep ocean. The deep ocean is not merely cold, it is not merely dark, it is a place where the physical assumptions of surface life cease to apply. Materials deform, gases vanish, metal bends. The very concept of empty space becomes meaningless because water fills everything, infiltrates everything, presses into every gap and cavity with a force that is constant, enormous, and absolutely indifferent. To bring the scale into sharper focus, consider what happens to a human body under these conditions. A recreational scuba diver typically descends no deeper than 30 to 40 meters. At 40 meters, the pressure is roughly 5 atmospheres. Even at this modest depth, the effects of pressure on the human body are significant. Gases in the blood absorb more nitrogen. The risk of nitrogen narcosis, a disorienting, intoxicating effect, sometimes called the rapture of the deep, increases. A return to the surface must be managed carefully to avoid decompression sickness. At 100 meters, the pressure is roughly 11 atmospheres, and the physiological challenges become severe. Below a few hundred meters, unprotected human descent is simply impossible. The body cannot withstand it, and the bottom of the Mariana Trench is more than 100 times deeper than the limit of the deepest recreational dives. The abyss does not merely resist human presence, it excludes it with a finality that no amount of willpower can overcome. Imagine if you could descend through the ocean in a glass elevator, watching as the world around you changed. For the first 200 meters, you would be in the epipelagic zone, the sunlight zone. This is where most of the ocean life familiar to us exists. Fish, coral reefs, sea turtles, dolphins, the vast floating meadows of phytoplankton that produce a significant portion of the oxygen in our atmosphere. Sunlight penetrates this zone, not all the way through it, but enough to drive photosynthesis, enough to support the complex food webs that underpin marine life near the surface. The colors are vivid here. Blues, greens, the flashing silver of schooling fish. This is the ocean of postcards and nature documentaries. Below 200 meters, you enter the mesopelagic zone, sometimes called the twilight zone. This extends to roughly 1,000 meters below the surface. Sunlight still reaches here, but just barely. It is the light of a fading sunset, blue shifting to grey, then to near black. At this depth, some light still filters down from above, but it is far too weak for photosynthesis. The creatures here have adapted to perpetual dusk. Many of them have enormous eyes, evolved to capture every last photon. Others have abandoned vision altogether and navigate by other means. Touch, the detection of pressure waves, the sensing of chemical traces dissolved in the water, and many produce their own light through bioluminescence, a chemical reaction within their tissues that generates cold, blue-green flashes in the darkness. In the twilight zone, the ocean begins to reveal its alien character. Life is not absent here, but it is life adapted to conditions that bear almost no resemblance to the surface. Below 1,000 meters is the bathypelagic zone, the midnight zone. It extends to roughly 4,000 meters. No sunlight reaches here. Not a single photon from the sun penetrates to this depth. The darkness is not the darkness of a room with the curtains drawn, where your eyes might adjust over time and begin to perceive shapes. It is the darkness of total absence. If you turned off every artificial light source in the midnight zone, you would see nothing. Absolute blackness in every direction, above, below, and on all sides. The only visible light in this entire layer of the ocean is produced by living things. Bioluminescent organisms flash and glow in the dark, creating brief, scattered points of cold light that appear and vanish like sparks in an infinite void. The temperature here hovers between 1 and 4 degrees Celsius. The pressure is immense, and yet organisms live here. They feed on the constant rain of organic material drifting down from the surface, a slow, unending snow of dead plankton, fish scales, and fecal pellets known as marine snow. This gentle, continuous fall of debris is the foundation of deep ocean food webs, the link that connects the sunlit surface to the midnight darkness below. Below 4,000 meters is the abyssopelagic zone, the abyss proper. This extends to roughly 6,000 meters and covers much of the deep ocean floor. The abyssal plains, vast flat expanses of sediment-covered seafloor, lie within this zone. These plains are among the flattest surfaces on the planet, flatter than any desert, any prairie, any salt flat on land. They are covered in a fine ooze of accumulated sediment, the compacted remains of billions of years of marine snow. The creatures here are adapted to extreme pressure, near freezing temperatures, and a food supply so sparse that survival requires extraordinary metabolic efficiency. Many abyssal organisms grow slowly, reproduce infrequently, and live for decades or even centuries. Life at these depths is not a frantic scramble for resources. It is a patient, slow, enduring persistence. And then there is the deepest zone of all, the Hadalpelagic zone, named after Hades, the ancient Greek realm of the dead. This zone exists only in the ocean trenches, the narrow gashes in the seafloor that plunge below 6,000 meters. The Hadal zone covers less than 1% of the total ocean floor, but it represents the most extreme conditions anywhere on the surface of this planet. The Mariana Trench, the Tonga Trench, the Kermadec Trench, the Philippine Trench, and a handful of others are the only places where the Hadal zone exists. The pressure at these depths is staggering. The isolation is total. Each trench is, in a biological sense, an island, cut off from the others by vast expanses of shallower water. Species that evolve in one trench may never encounter species from another. The Hadal zone is not one habitat. It is a collection of separate habitats, each one a tiny, high-pressure world unto itself. And yet, even here, life has been found. Amphipods, small crustaceans resembling shrimp, have been collected from Hadal depths. These creatures are not merely surviving, they are thriving, occurring in densities that surprised the first researchers to discover them. Sea cucumbers have been filmed crawling across the sediment at the bottom of the deepest trenches. Their soft, translucent bodies somehow enduring pressures that would crush machinery. Microbial communities thrive in the sediment, sustained by chemical energy rather than sunlight, metabolizing compounds that would be useless on the surface. Xenophyrophores, single-celled organisms that can grow to the size of a human fist, carpet parts of the Hadal floor in some regions. Fewer humans have visited these depths than have orbited the Earth in spacecraft, and yet they are not empty. They are inhabited, and their inhabitants, whatever sounds they might produce, have been calling into the darkness for longer than anyone has been listening. The point of describing these zones is not merely to catalogue the layers of the ocean. It is to establish something fundamental about the medium through which the sounds from the abyss travel. Light fails in the ocean. Within a few hundred meters, it is gone. Vision, the sense that dominates human experience, is useless in the deep sea. But sound does not fail. Sound does not stop at the boundary between the twilight zone and the midnight zone. Sound does not fade to black at 1,000 meters and disappear. Sound travels through all of these zones, from the sunlit surface to the Hadal trenches and back again. Sound is the one form of energy that connects every layer of the ocean into a single, continuous acoustic space. and it does so with extraordinary efficiency. Sound travels through seawater approximately 4.3 times faster than it travels through air. In air, sound moves at roughly 343 meters per second. In seawater, it moves at roughly 1,500 meters per second, though this speed varies with temperature, salinity, and pressure. The density of water, roughly 800 times the density of air, makes it an extraordinarily effective medium for transmitting acoustic energy. Sound waves in water lose energy more slowly than sound waves in air. They travel farther. They maintain their coherence over longer distances. A sound that would fade to inaudibility after a few kilometers in air can travel thousands of kilometers in the ocean, with enough energy remaining to be detected by sensitive instruments. The ocean is, in acoustic terms, a conductor of astonishing quality. But there is a feature of the ocean that takes this efficiency and amplifies it to something almost unbelievable. It is called the SOFAR channel. SOFAR stands for sound fixing and ranging. It is a horizontal layer within the ocean, typically found at depths between roughly 600 and 1,200 meters, where the speed of sound reaches a minimum value. This minimum occurs because of two competing physical effects. Near the surface, the water is warm, and warm water conducts sound faster. As you descend, the temperature drops, and the speed of sound decreases. But below a certain depth, the temperature stabilizes, while the pressure continues to increase. And increased pressure raises the speed of sound. At the depth where the downward effect of decreasing temperature and the upward effect of increasing pressure exactly balance, the speed of sound hits its lowest point. That depth is the axis of the SOFAR channel. The physics of what happens next is elegant in its simplicity and extraordinary in its consequences. Sound produced within the SOFAR channel tends to remain within it. If a sound wave moves upward from the channel axis, it enters water where the speed of sound is higher. The wave bends back downward, refracted by the gradient in sound speed, much as a beam of light bends when it passes from air into water. If the wave moves downward from the axis, the same thing happens in reverse. It enters water where the speed of sound is higher due to increased pressure, and it bends back upward. The result is that sound becomes trapped in this channel, oscillating up and down around the axis, traveling vast horizontal distances with minimal loss of energy. The effect is not subtle. A relatively modest sound produced within the SOFAR channel can propagate across an entire ocean basin with enough energy remaining to be clearly detected by a sensitive hydrophone. A low-frequency pulse generated in the Central Pacific can be detected on a hydrophone off the coast of North America. A sound produced near Antarctica can be recorded near the equator. The distances are not hundreds but thousands of kilometers. During the Second World War, researchers demonstrated that a small explosive charge detonated at the correct depth in the Atlantic could be detected by hydrophones more than 3,000 kilometers away. The signal arrived weakened, but still clearly distinguishable from the background noise. The SOFAR channel turns the ocean into a kind of global telephone line for low-frequency sound, a waveguide of planetary scale. The implications are profound. An animal calling in one part of an ocean basin can potentially be heard by another animal on the far side of that basin. A geological event on one mid-ocean ridge can be acoustically detected from the other side of the world, and a mysterious sound produced by an unknown source in one region of the deep Pacific can arrive, loud and clear, at a hydrophone station thousands of kilometers away, carrying with it the spectral fingerprint of its origin, but none of the visual evidence that might identify it. The SOFAR channel does not merely facilitate long-range sound transmission. It creates a situation in which sounds can be heard without their sources being locatable in any practical sense. Detection becomes trivially easy. Identification becomes almost impossibly hard. This phenomenon was first understood during the Second World War, though its implications were quickly recognized and classified. During the 1940s, American physicist Maurice Ewing and his colleague Joe Wurzel proposed that the SOFAR channel could be used to detect the sounds of explosions at long range. They conducted experiments in which small charges were detonated in the ocean and detected by hydrophones thousands of kilometers away. The results confirmed that the channel existed and functioned as predicted. The military application was immediately apparent. If you could detect the sound of a distant explosion, you could also detect the sound of a distant submarine. And so began one of the most ambitious listening programs in the history of technology. The United States Navy built the sound surveillance system known as SOSUS. This was a network of fixed hydrophone arrays installed on the ocean floor at strategic locations across the Atlantic and Pacific Oceans. The hydrophones were connected to shore-based processing centers by undersea cables that ran for hundreds, sometimes thousands, of kilometers along the continental shelves. The first SOSUS stations became operational in the early 1950s. Over the following 2 decades, the network expanded to cover the major submarine transit routes in the North Atlantic, the Norwegian Sea, the Western Pacific, and other key areas. Each station consisted of an array of individual hydrophones, spaced at precise intervals, connected to amplifiers and signal processing equipment on shore. By analyzing the time delay between a sound arriving at different hydrophones in an array, operators could determine the direction from which the sound had come. By combining data from multiple stations, they could triangulate the location of a sound source with considerable accuracy. The system was one of the most closely guarded secrets of the Cold War. Its existence was classified. Its locations were classified. Its capabilities were classified. The personnel who operated it were forbidden from discussing their work. For decades, SOSUS was a vast, invisible ear pressed against the ocean floor, straining to hear the distant hum of a Soviet submarine's propeller turning in the dark. During the Cuban Missile Crisis of 1962, SOSUS played a role in tracking Soviet naval movements. Throughout the 1970s and 80s, it was a cornerstone of American anti-submarine warfare strategy, providing early warning of Soviet submarine deployments and enabling the Navy to maintain situational awareness across vast stretches of ocean. For decades, SOSUS operated in secrecy. The data it collected was classified. The recordings were analyzed by military personnel and intelligence analysts, not by scientists. The ocean sounds captured by the system, sounds that included not only submarine signatures but also whale calls, seismic events, volcanic eruptions, and countless other acoustic phenomena, were locked away behind security clearances and need-to-know restrictions. The military was listening to the ocean, but the military was listening for a very specific thing, and everything else was, at best, background noise to be filtered out, at worst, a nuisance that cluttered the acoustic picture. Then the Cold War ended. The Soviet Union dissolved in 1991. The strategic rationale for SOSUS diminished virtually overnight. The vast network of underwater listening stations, built at enormous expense over 4 decades, faced an uncertain future, and gradually, tentatively, the scientific community gained access. Oceanographers and marine biologists had long suspected that the deep ocean was acoustically rich, but they had lacked the infrastructure to prove it. SOSUS offered exactly what they needed: a pre-existing, globally distributed, exquisitely sensitive listening network already in place, already operational, already funded. The transition was not instantaneous, and military restrictions on the most sensitive data persisted. But by the mid-1990s, civilian scientists were using SOSUS and SOSUS-derived data to study the ocean in ways that had never before been possible. And what they heard was staggering. The ocean was not quiet. It had never been quiet. It was a world of continuous, overlapping, competing sound. Blue whales sang in frequencies so low they were below the range of human hearing, yet so powerful they crossed entire ocean basins. Fin whales produced rhythmic pulses that could be detected thousands of kilometers from their source. Sperm whales clicked in patterns that researchers suspected were individualized, a kind of acoustic signature unique to each animal. Earthquakes along mid-ocean ridges produced sudden bursts of low-frequency energy that lit up spectrograms like fireworks. Icebergs calving from Antarctic glaciers sent shockwaves through the water that were detected in the tropics. Ship traffic hummed in the background, a constant low-frequency drone that had been increasing in intensity for decades as global commerce grew. And mixed in with all of these known, identifiable sounds, there were other signals that did not match any template. signals that could not be attributed to any known whale, any known geological process, any known human activity. They appeared on spectrograms as distinct, vivid patterns, sweeping curves, pulsing lines, steady drones, abrupt bursts, shapes that stood out clearly from the background noise, but that matched nothing in the existing catalogues. These were the sounds that would come to be known by their simple, evocative names. The bloop, the upsweep, the slowdown, Julia, the train, the whistle, and many more, unnamed, uncatalogued, sitting in archives on aging magnetic tapes and digital storage devices. NOAA expanded the listening program in the 1990s, deploying autonomous hydrophone arrays in the equatorial Pacific and elsewhere. These were independent stations, not connected to SOSUS, designed specifically for scientific research rather than military surveillance. Each autonomous station consisted of a hydrophone suspended in the water column, typically near the SOFAR channel axis to maximize detection range, connected to a recording package anchored to the seafloor. The recording packages operated on battery power and stored data on internal hard drives. Periodically, research vessels would visit each station to replace batteries, swap hard drives, and service the equipment. Between visits, the stations recorded continuously, 24 hours a day, 7 days a week, month after month. The result was datasets of extraordinary size and continuity, comprehensive records of everything the ocean produced acoustically in the vicinity of each station. Researchers at NOAA's Pacific Marine Environmental Laboratory, led by scientists including Christopher Fox and Robert Zayak, began systematically analyzing these recordings. They used spectrogram analysis, a method that displays sound as a visual graph of frequency plotted against time, with the intensity of each frequency represented by color. On a spectrogram, a whale call appears as a distinctive curve sweeping through specific frequencies. A ship propeller appears as a broad, smudged bar across many frequencies simultaneously. An earthquake appears as a sudden, explosive burst of low-frequency energy. Each type of sound has a characteristic visual signature, a shape on the spectrogram that an experienced analyst can recognize at a glance. And then there were the other signatures, the ones that did not match. The ones that appeared as vivid, distinct patterns on the spectrograms, but that corresponded to nothing in the existing catalogues. Sweeping curves that climbed through frequencies no known animal could produce. Steady lines that persisted for minutes, hours, or days at a time. Abrupt bursts that appeared, flared brightly across a range of frequencies, and then vanished as quickly as they had come. These signals were not noise. They were not artifacts of equipment malfunction or data processing errors. They were real acoustic events, produced by real sources, transmitted through real water, and captured by real instruments, and their sources were unknown. The catalogue of unidentified signals continued to grow. Each year, the autonomous stations added hundreds of hours of new recordings. Each batch of data, when analyzed, revealed not just more of the same known sounds, but new unknown ones. The ocean, it seemed, had a far larger vocabulary than anyone had imagined, and we had only begun to learn a few of its words. The science of underwater acoustics was mature enough to detect these sounds with extraordinary precision. The SOFAR channel was well understood. The propagation characteristics of low-frequency sound in seawater were well modeled. The hydrophones were sensitive, reliable, and well-calibrated. The problem was not detection. It was identification. The instruments could tell you that a sound existed, what frequencies it contained, how long it lasted, how powerful it was, and approximately where it originated. But they could not tell you what made it. That required something more. It required either observing the source directly or matching the recorded signal to a sound whose origin was already known. And for many of the signals in the catalogue, neither condition had been met. The ocean had been speaking all along. It had been producing these sounds for far longer than any human technology had existed to record them. The SOFAR channel had been guiding them across ocean basins since long before Maurice Ewing proposed his theory in the 1940s. The creatures in the deep had been calling, clicking, groaning, and roaring in the darkness since long before the first hydrophone was lowered into the water. What changed was not the ocean. What changed was our ability to hear it. And what we heard, once we began to listen, was far more complex, far more powerful, and far more mysterious than anyone had expected. The scale of this acoustic world cannot be overstated. The ocean floor stretches across more than 360 million square kilometers. The mid-ocean ridge system alone runs for more than 65,000 kilometers through every major ocean basin, a chain of volcanic mountains longer than any feature on dry land. Seamounts, underwater mountains that do not reach the surface, number in the tens of thousands, and many of them have never been surveyed. Submarine canyons cut deep grooves into the continental slopes, channeling sediment and water in ways that can generate their own acoustic signatures. Every one of these features is a potential source of sound. Every one of them exists in an acoustic medium of extraordinary efficiency, and every one of them is, for the most part, unmonitored. The gap between what the ocean produces and what we record is immense. The autonomous hydrophone arrays cover a fraction of the total ocean area. Vast stretches of the Indian Ocean, the Southern Ocean, the South Atlantic, and the Arctic have no dedicated acoustic monitoring whatsoever, even in the equatorial Pacific, where NOAA's coverage is densest. The distance between adjacent stations is typically hundreds or thousands of kilometers. A sound produced in the gap between two stations might be detected by both, but with reduced directional accuracy and limited ability to triangulate its origin. A sound produced far from any station might not be detected at all. We are listening to the ocean through a handful of keyholes, and what we hear through those keyholes is already overwhelming. Then something happened that changed everything. In a single year, 1997, the NOAA hydrophone arrays in the Pacific recorded a cluster of signals that would transform the field of deep ocean acoustics and capture the imagination of the public in a way that no previous underwater recording had ever done. The sounds from the abyss had been heard, and the world was about to learn that the deep ocean had a voice. The core problem is simple to state and profoundly difficult to resolve. The ocean produces sounds that our best instruments can detect, that our best analysts can describe in precise acoustic detail, and that our best scientists cannot conclusively explain. These are not vague signals buried in noise. They are distinct, often powerful, sometimes repeating acoustic events with clear spectral signatures. They show up on spectrograms as vivid, unmistakable patterns. They have been recorded independently by multiple hydrophone stations separated by thousands of kilometers. They are real, and many of them remain, in the strictest scientific sense, unidentified. To understand the weight of that statement, consider what it means for a sound to be unidentified in this context. It does not mean that no one has looked at it. It means that experts in underwater acoustics, people who have spent careers studying the sounds of the ocean, have examined the spectral signature, compared it to every known source in their databases, applied mathematical models, consulted with colleagues in geology, biology, and physics, and still cannot say with certainty what produced the sound. It means the sound falls outside the boundaries of current knowledge, not outside the boundaries of current imagination, because there is no shortage of hypotheses, but outside the boundaries of what can be confirmed. The most famous of these unidentified sounds is the bloop. On the 19th of June, 1997, the NOAA Equatorial Pacific Autonomous Hydrophone Array detected an ultra-low frequency sound of extraordinary power. The sound was captured by multiple sensors. It was detected by hydrophones separated by more than 5,000 kilometers, which tells us two things: that the sound was extremely loud, and that it propagated through the SOFAR channel with the efficiency that channel provides. The sound itself lasted roughly 1 minute. It rose rapidly in frequency, sweeping upward through the low-frequency band before cutting off abruptly. When researchers at the Pacific Marine Environmental Laboratory examined the spectrogram, they saw a clear, coherent signal, not a messy smear of noise, but a structured acoustic event with a definite beginning, a definite shape, and a definite end. The amplitude was what drew the most attention. Early analyses estimated that the source of the bloop was far louder than the loudest known biological sound. The blue whale, the largest animal currently living on this planet, can produce calls reaching approximately 188 decibels. The bloop appeared to be significantly louder than this. For context, decibels in water are not directly comparable to decibels in air. and the physics of underwater sound transmission means that the same decibel value represents a different amount of energy in water than in air. But even accounting for these differences, the raw acoustic power of the bloop was enormous. Something produced it, and that something was either very large or very close to the hydrophone, or operating with a mechanism of sound production unlike anything in the existing literature. The name came from the researchers themselves. Christopher Fox, who led the acoustic monitoring program at NOAA's Pacific Marine Environmental Laboratory, is credited with naming many of the unidentified sounds. When the bloop signal was sped up to a frequency range audible to the human ear, playing back in seconds what had originally occurred over a minute, it sounded like a deep, wet, resonant pulse, a blooping noise that had a disturbingly organic quality. It sounded alive. It sounded biological. And that impression, combined with its extraordinary amplitude, is what made the bloop a global sensation when it was eventually reported to the public. The media coverage was predictable and in its way understandable. Here was a sound from the deep ocean, louder than any known animal, with a biological quality that even the scientists who discovered it acknowledged. The parallels to sea monster legends were irresistible. Journalists noted that the estimated origin of the bloop in the southern Pacific Ocean was not far from the fictional coordinates of R'lyeh, the sunken city described in the horror fiction of H.P. Lovecraft, where a monstrous being slumbers beneath the waves. This was, of course, pure coincidence. The Pacific Ocean is vast, and any randomly chosen point in it is not far, in oceanic terms, from some fictional location or another. But the coincidence delighted those who enjoy the overlap of science and mythology, and it cemented the bloop in popular culture as a symbol of the ocean's capacity for mystery. The scientific community's reaction was more cautious, but no less engaged. The bloop's spectral profile bore some resemblance to known biological signals. The way it swept upward in frequency was reminiscent of certain whale vocalizations. Its temporal structure, with a clear onset, a peak, and a cessation, looked more like a call than a geological event. But the amplitude problem was severe. If the bloop was biological in origin, it implied the existence of an organism significantly larger than any species known to science. The blue whale, at lengths of up to 30 meters or more, is already the largest animal on the planet. For a creature to produce a sound substantially louder than a blue whale call, it would presumably need to be substantially larger than a blue whale, or it would need a sound-producing mechanisms of extraordinary efficiency, something not seen in any known marine organism. Neither of these possibilities had supporting evidence. No carcass of a giant unknown species had ever been found. No specimen had been collected. No secondary evidence, no sightings, no photographs, no genetic traces in environmental DNA samples pointed to the existence of such a creature. For years, the bloop occupied a peculiar position in the scientific literature. It was too well documented to be dismissed. It was too anomalous to be easily explained. It sat in a kind of limbo, a genuine data point that resisted comfortable categorization. Researchers continued to study it, comparing its spectral signature to known sources, running models, proposing hypotheses, and gradually the evidence shifted. In 2005, NOAA researchers published analyses suggesting that the bloop was consistent with the sounds produced by large-scale ice events, specifically the fracturing and calving of Antarctic ice sheets. When a massive section of an ice shelf cracks and breaks away from the continent, the resulting sound can be enormous, a deep, resonant burst of acoustic energy that propagates through the SOFAR channel across thousands of kilometers. The spectral characteristics of such events, when modeled carefully, showed a close match to the bloop. The estimated origin region in the southern Pacific was geographically plausible for an Antarctic source. Subsequent analyses, using improved propagation models and comparison with additional recordings of confirmed ice events, strengthened the ice hypothesis. By the early 2010s, the scientific consensus had shifted firmly. The bloop was almost certainly an icequake, the sound of an enormous piece of Antarctic ice breaking free. The key evidence came from comparison. Researchers had recorded the sounds of known ice calving events, where satellite imagery confirmed the timing and location of a specific ice fracture and then compared these confirmed recordings to the Bloop. The spectral match was strong. The frequency range, the temporal shape, the rate of frequency change all aligned. It was not a perfect match, because no two ice events are identical, but it was within the range of variation expected for natural processes of that type. The scientific community, while noting residual uncertainties, accepted the ice explanation as the most parsimonious account of the data. The resolution of the Bloop brought a certain satisfaction. A famous mystery had been solved, or at least resolved to the satisfaction of the scientific community. But the resolution also carried a quiet disappointment, a sense that the most evocative hypothesis, the idea of an unknown leviathan in the deep, had been set aside in favor of a geological explanation. The ocean was not harboring a creature larger than anything known to science. It was simply breaking ice. The romantic possibility had yielded to the prosaic reality, but there was also a deeper lesson in the Bloop's resolution. It demonstrated that acoustic identification in the deep ocean is not impossible. It showed that patient, methodical comparison of unknown signals to known sources can eventually yield results. It proved that the catalogue of the unexplained can, given enough time and data, become a catalogue of the explained. But it also showed how long the process takes. The Bloop was recorded in 1997. Its ice attribution was first proposed in 2005. The consensus solidified over the following several years. A single sound, one of the most studied underwater signals ever recorded, required nearly a decade of analysis before a widely accepted explanation emerged. If the timeline for explaining one prominent sound is measured in years and decades, the timeline for explaining the entire catalogue of unknown signals is measured in generations. And yet, the resolution of the Bloop solved only one puzzle. The catalogue of unidentified sounds contained many other entries, and these were not so easily explained. Consider the Upsweep. First detected in August of 1991, the Upsweep is a narrowband sound consisting of a long series of upsweeping tones, each lasting several seconds. The overall signal can persist for extended periods. It was detected across the Pacific Ocean, recorded by multiple hydrophone stations, suggesting that the acoustic energy involved was substantial. What makes the Upsweep particularly distinct is its apparent seasonality. Its intensity varies over the course of the year, peaking in the spring and autumn. Some researchers have noted a possible correlation with the equinoxes, though the statistical significance of this correlation is debated. The estimated source region lies in the South Pacific, near the location of known volcanic activity on the Pacific-Antarctic ridge. This has led to the leading hypothesis that the Upsweep is produced by volcanic or hydrothermal activity on or near the ridge, perhaps the resonances of gas or magma interacting with seawater in some as yet uncharacterized way. But no specific volcanic feature has been identified as the source. No expedition has visited the proposed source region to investigate. And the Upsweep continues, more than 3 decades after it was first recorded, recurring with its characteristic seasonal pattern, a sound that has outlasted the careers of many of the scientists who first studied it. The slowdown was recorded on the 19th of May, 1997, the same year as the Bloop, in what was clearly a remarkable year for unexplained ocean acoustics. The slowdown is a sound that gradually decreases in frequency over a period of roughly 7 minutes. It is a descending tone, a long, slow fall through the frequency spectrum that gives the sound its name. It was detected across the entire Pacific basin, meaning that multiple hydrophone stations, separated by thousands of kilometers, all picked up the same signal at times consistent with acoustic propagation from a common source. The power required to produce a signal detectable at that range is immense. The leading hypothesis attributes the slowdown to the friction of a large mass of ice, possibly an iceberg or a section of ice shelf, grinding against the seafloor or against the continental shelf near Antarctica. The slow descent in frequency would correspond to the gradual deceleration of the ice mass as friction slowed its movement. It is a plausible explanation, consistent with what we know about the acoustics of ice rock friction, but it remains a hypothesis. No direct observation of the event has ever been made. no expedition has corroborated the proposed mechanism. The slowdown was recorded, analysed, and hypothesized about, and there the story pauses. Julia was detected on the 1st of March 1999. It is a strange, eerie sound lasting approximately 15 seconds, with a complex spectral signature that includes both rising and falling tones. When the recording is sped up and played at frequencies the human ear can perceive, it sounds haunting, almost mournful, a rising wail that fades into silence. The name Julia was given by NOAA researchers, continuing the tradition of assigning human or evocative names to unidentified signals. The sound was detected across the equatorial Pacific, recorded by multiple stations, with enough power to confirm that it was a significant acoustic event and not merely local noise. NOAA attributed Julia to the sound of a large Antarctic iceberg running aground and scraping along the seafloor. The attribution is plausible. Large icebergs can produce a wide range of sounds as they interact with the ocean floor, from low rumbles to high-pitched squeals, depending on the speed, mass, and nature of the contact. But as with the slowdown, the attribution rests on acoustic modelling and circumstantial evidence rather than direct observation of the source event. The iceberg was never identified. Its grounding was never confirmed by satellite imagery or other means. Julia is an explanation that fits the data but has not been independently verified. And this pattern of plausible explanations that fit the data without being confirmed by independent evidence repeats throughout the catalogue. It is the defining characteristic of deep ocean acoustic science at its current stage of development. We are very good at generating hypotheses. We are far less good at testing them. The ocean provides the sounds, it does not provide the confirmation. There is something worth pausing to consider here. We are a species that has built particle accelerators to study the smallest constituents of matter. We have constructed telescopes that can detect photons that have been traveling since the earliest epochs. We have sequenced our own genetic code and built machines that can edit it with precision. And yet, when a sound rises from the bottom of our own ocean, a sound so loud it crosses 5,000 kilometers and registers on military-grade instruments, we often cannot say what made it. This is not a failure of science, it is a measure of ocean. The deep sea is not an environment that yields its secrets easily. It resists, it withholds. It demands a level of effort and patience and investment that our civilization has not yet been willing to provide. The train is another entry in the catalogue. Recorded in the Pacific Ocean, the train is a steady, low-frequency sound that persists for extended periods, sometimes hours at a time. It has a monotonous, droning quality that, when played back to human ears, evokes the rumble of a distant locomotive rolling along tracks, hence the name. Its spectral signature is relatively simple, a sustained tone at a consistent frequency, without the complex sweeping or pulsing seen in some of the other unidentified sounds. The consistency of the signal suggests a source that is either continuously active or that produces sound over long intervals. Like the Upsweep, the train has been provisionally linked to volcanic or geothermal activity, perhaps the sustained emission of gas or heated fluid from a vent or fissure on the ocean floor, but the specific source has never been identified. The proposed mechanism has never been directly observed, and the train continues to appear in recordings, a patient, steady presence in the acoustic record, utterly indifferent to the absence of an explanation. The whistle was detected in the Pacific Ocean in July of 1997. It consists of a series of narrowband tones that sweep downward in frequency. It does not match any known marine biological call. It does not match standard templates for geological sound sources. Its duration was relatively brief, and it has not been consistently detected in subsequent years, making it one of the more enigmatic entries in the catalogue. A sound that appeared once, or a few times, and then vanished. It may have been a one-time event, an ephemeral acoustic phenomenon that will never recur, or it may recur at intervals that are longer than our recording history, or it may have been produced by a source that has since changed or moved or ceased to exist. Without a confirmed identification, any of these possibilities remains open. Beyond these signals, there are other acoustic mysteries in the ocean that, while not unidentified in the same technical sense, highlight the strangeness of the deep-sea acoustic world. Consider the case of the so-called 52 Hertz whale. Since 1989, researchers at the Woods Hole Oceanographic Institution detected the calls of a whale at an unusual frequency. Most baleen whales call at frequencies between 12 and 25 Hertz. This individual called consistently at approximately 52 Hertz, a frequency far higher than any known whale species. The call pattern was consistent with a baleen whale. It followed migratory routes typical of baleen species, and it repeated seasonally. But no whale of any known species calls at that frequency. The animal was tracked acoustically for more than a decade. Its calls recorded year after year, its migratory path mapped in detail, and yet it was never visually identified. It was never photographed. It was never approached by a research vessel. The 52 Hertz whale became a cultural phenomenon, widely described as the loneliest whale in the world. Its calls supposedly inaudible to other whales and therefore unanswered. The reality is likely more nuanced. Recent research suggests that some whale species can hear a wider range of frequencies than previously thought, and the 52 Hertz whale may not have been as isolated as the popular narrative implied. But the case illustrates a crucial point. Even when a sound is clearly biological, even when it is recorded repeatedly over many years, even when its source is almost certainly a single identifiable animal, the deep ocean can still prevent us from determining exactly what that animal is. The acoustic world of the ocean is one in which sources can be heard but not seen, tracked but not identified, studied for years, and still not fully understood. There is also the phenomenon known as the chorus, or dawn chorus, of the deep sea. In many parts of the ocean, hydrophones detect a noticeable increase in biological sound at dawn and dusk, a swelling of clicks, pops, groans, and other noises that coincides with the daily vertical migration of deep-sea organisms. Each evening, billions upon billions of creatures rise from the deep toward the surface to feed under cover of darkness, and each morning they descend again to the safety of the depths. This massive movement, the largest animal migration on the planet by biomass, is accompanied by a corresponding surge in acoustic activity that can raise the overall sound level by several decibels. The individual sounds that make up this chorus come from a wide variety of sources, many of which have been identified. The snapping of pistol shrimp producing shock waves hot enough to briefly exceed the temperature of the surface of the sun. The drumming of certain fish species vibrating specialized swim bladders. The clicks of small squid navigating through the dark. But within the chorus there are components that remain unidentified, individual sound types that contribute to the overall acoustic picture, but that have not been attributed to any specific organism. These unidentified components of the chorus are not as dramatic as the bloop or the upsweep. They do not generate headlines, but they are a persistent daily reminder that the acoustic biology of the deep ocean is far from fully catalogued. The problem extends to the geological realm as well. The ocean floor is not a quiet, stable surface. It is in constant motion, shaped by forces that operate on timescales ranging from seconds to millions of years. Tectonic plates grind past each other along transform faults. Magma rises through the crust at spreading centers and erupts, sometimes explosively, into the cold water above. Submarine landslides send cascades of sediment tumbling down continental slopes, generating turbidity currents that flow across the abyssal plains at speeds of tens of kilometers per hour. Gas hydrates, crystalline structures of methane and water ice locked in deep-sea sediments, can suddenly destabilize and release enormous volumes of methane gas, which bubbles upward through the water column, in events that can be both sudden and acoustically dramatic. Each of these geological processes produces sound. Some have been well characterized. The acoustic signatures of certain types of earthquakes are well understood and can be identified automatically by computer algorithms. The sounds of some volcanic eruptions have been recorded and analyzed, but many geological sound sources have been characterized only partially or not at all. A submarine landslide in an unmonitored part of the ocean might produce a powerful acoustic signal that propagates through the SOFAR channel and arrives at a distant hydrophone station as an unidentified transient event. A methane release from an unstable hydrate deposit might generate a distinctive acoustic signature that has never been recorded under controlled conditions. A previously unknown volcanic vent might begin erupting, producing sounds that are novel in the acoustic record, simply because no one has ever listened to that particular vent before. The interaction between water, rock, gas, and ice in the deep ocean creates an acoustic environment of almost limitless complexity. Sound sources are numerous, varied, powerful, and often transient. They occur at depths that are inaccessible to direct observation. They occur in locations that are unmonitored. They occur under physical conditions, extreme pressures, near freezing temperatures, total darkness that cannot be easily replicated in a laboratory. And when the sounds they produce travel thousands of kilometers through the SOFAR channel and arrive at a hydrophone array, they carry with them the spectral fingerprint of their origin, but none of the visual, physical, or chemical evidence that would be needed to confirm an identification. And it gets worse. Because these named, catalogued sounds are merely the prominent entries in a much larger archive of unexplained signals. The recordings collected by NOAA and by the remnants of the SOSUS network contain thousands of transient signals, brief bursts of sound that appear once or a handful of times and then disappear. Many of these signals are too short or too faint to warrant individual attention. They sit in the data unexamined. They have not been named. They have not been published. They have not been the subject of press releases or media stories. But they are there. Every year, the autonomous hydrophone stations add hundreds of hours of new recordings to the archive. Every year, the data grows, and with each passing year, the gap between the volume of recorded data and the capacity of the scientific community to analyze it widens. The situation is sometimes compared to trying to read a vast library in which new books arrive faster than you can read. The library grows, the number of readers does not, and so the unread volumes accumulate on the shelves, each one potentially containing information that could change our understanding of the ocean, but each one also competing for attention with thousands of others. The resources available for deep-sea acoustic research are limited. The number of trained analysts who can interpret spectrograms and assess unknown signals is small. The funding for expeditions to investigate sound sources is scarce. The result is a growing archive of the unknown, a collection of acoustic recordings that represents one of the most comprehensive records of the deep ocean's voice ever assembled, and that is being analysed at a pace that is, by any objective measure, inadequate to the task. There is a concept in acoustics called the noise floor, the level of background noise below which individual signals cannot be reliably distinguished. In the deep ocean, the noise floor is shaped by a combination of sources. Distant shipping traffic, whose low-frequency hum has been increasing for decades as global maritime commerce has expanded. Seismic activity along tectonic boundaries. Biological sounds from whales, dolphins, fish, and invertebrates. And the constant low murmur of wind-driven surface waves far overhead. Against this background, a signal must be sufficiently loud, sufficiently distinct in frequency, and sufficiently different from the ambient noise to be identified as a discrete acoustic event. The noise floor itself has been changing over time. The amount of commercial shipping on the world's oceans has increased dramatically since the mid-20th century. Each ship produces low-frequency noise from its engines and propellers, and the cumulative effect of thousands of ships operating simultaneously has raised the background noise level in the ocean by a measurable amount. Some studies estimate that ambient ocean noise in the low-frequency bands has increased by roughly 3 decibels per decade since the 1950s, which corresponds to a doubling of acoustic energy every 10 years. This rising noise floor has consequences for both the animals that use sound to communicate and the scientists who use hydrophones to listen. As the noise floor rises, quieter signals become harder to detect. Sounds that might have been identifiable against a quieter background become lost in the increasing hum of human activity. It is possible, even likely, that there are mysterious ocean sounds occurring right now that cannot be detected because the noise of our own civilization is drowning them out. Many of the unidentified sounds that have been recorded meet all of the criteria for clear detection, despite this rising noise floor. They stand out clearly from the background. They are not artifacts of equipment malfunction or digital processing errors. They are real signals produced by real sources, and their sources remain unknown. The challenge of identification is compounded by the sheer inaccessibility of the deep ocean. When a mysterious sound is detected, and its origin is estimated, using time of arrival differences across multiple hydrophone stations, to lie at some point in the mid-Pacific, what happens next? In theory, an expedition could be launched. A research vessel could sail to the estimated location. Instruments could be lowered. Cameras could be deployed. The source could be identified. In practice, such an expedition would cost millions of dollars. It would require weeks or months of planning. The ship would need to carry specialized deep-sea equipment, remotely operated vehicles, deep-rated cameras, additional hydrophones for close-range listening. The vessel would need to reach a location that might be thousands of kilometers from the nearest port, and even if all of this were accomplished, there is no guarantee of success. The sound might have stopped by the time the vessel arrives. The source might have moved, particularly if it is biological. The origin estimate might be imprecise, off by tens or even hundreds of kilometers, because the triangulation depends on assumptions about the speed of sound and the propagation path that may not hold perfectly over such vast distances. And even if the vessel reached exactly the right spot, the source might be at a depth that exceeds the operational limits of available submersibles or remotely operated vehicles. The deepest rated scientific remotely operated vehicles can reach depths of approximately 6,000 to 7,000 meters. Below that, only a handful of specialized vehicles can operate, and access to them is extremely limited. The deep ocean resists investigation with a patience and a totality that makes terrestrial research seem trivially easy by comparison. On land, a mysterious sound can often be investigated simply by walking to its source and observing. In the air, an unidentified acoustic signal can be traced by radio direction finding and potentially matched to an aircraft or atmospheric phenomenon. In the ocean, a mysterious sound can be recorded with extraordinary precision and still remain forever unexplained, simply because the source is unreachable. This asymmetry between the ease of detection and the difficulty of identification is the central tension of deep ocean acoustics. It is the reason the catalogue of unexplained sounds continues to grow, year after year, decade after decade, with no sign of reaching a point where the explanations catch up. There is another dimension to this problem that touches on the very nature of acoustic identification. The process of identifying an unknown sound depends on comparison. An analyst examines a spectrogram and compares its features to a database of known sounds. If the frequency pattern matches a blue whale call, it is labeled accordingly. If it matches the signature of a seismic event, it is categorized as geological. If it matches the known acoustic profile of a specific species of fish, or a particular type of ice event, or the cavitation noise of a ship propeller, it is assigned to that category. The system works well for sounds that have been previously recorded and characterized under controlled or well-understood conditions. It works well for sounds that fall within the boundaries of existing knowledge. But what happens when a sound does not match anything in the database? The analyst can propose hypotheses. The sound might be a known source behaving unusually. It might be a combination of multiple known sources whose overlapping signals create a novel pattern. It might be a known type of event occurring in an unexpected location. These are all reasonable possibilities, and experienced analysts weigh them carefully. But they are hypotheses, not identifications. They are informed guesses, constrained by the limits of what has already been catalogued. Consider the mid-ocean ridge system. This chain of submarine volcanic mountains runs through every major ocean basin for more than 65,000 kilometers. It is the longest geological feature on the planet, far longer than any mountain range on land. Along its length, new ocean floor is continuously being created as magma rises from the mantle, solidifies, and pushes the existing sea floor apart. The ridge system is a site of constant geological activity. Earthquakes occur along it regularly, ranging from barely detectable microtremors to powerful events that register on seismographs worldwide. volcanic eruptions, both explosive and effusive, take place beneath thousands of meters of water. Hydrothermal vents, openings in the seafloor where superheated, mineral-rich water erupts into the cold, deep line segments of the ridge. Each of these processes produces sound. Some of these sounds have been characterized. Earthquake signatures along mid-ocean ridges are well understood. The sounds of certain types of volcanic eruptions have been recorded, but the ridge system is vast, and much of it has never been acoustically monitored at close range. There are almost certainly sounds being produced along the ridges that have never been recorded under conditions that would allow them to be identified. When these sounds arrive at a distant hydrophone, they are unfamiliar, they do not match the database, and they join the growing catalogue of the unexplained. The same principle applies to seamounts, the thousands of underwater mountains scattered across the ocean floor. Some seamounts are volcanic and currently active, others are extinct but still interact acoustically with the currents, tides that flow around and over them. The interaction of moving water with the complex topography of a seamount can generate sound, much as wind blowing across a mountain pass can produce an audible whistle or roar. Ocean currents, forced through narrow passages or over sharp ridges, can create turbulent flow patterns that produce acoustic signatures. Very few seamounts have been acoustically studied in any detail. The total number of seamounts in the world's oceans is estimated to be in the range of 100,000 or more, and only a small fraction have been surveyed, let alone monitored with hydrophones. Each unmonitored seamount is a potential source of unknown sound, a potential contributor to the catalogue of the unexplained. The Antarctic region presents its own set of acoustic complexities. The ice sheets that surround the southern continent are in constant motion, flexing, fracturing, calving, and grinding against the continental shelf and the seafloor below. The sounds produced by Antarctic ice are extraordinarily varied. A single large iceberg, drifting with the ocean currents, can produce a symphony of acoustic events over its lifetime. Low-frequency booms when internal stresses cause it to crack, high-pitched squeals when it scrapes against the seafloor or against other ice, sustained rumbles when it rolls or overturns, and broadband crashes when pieces calve from its sides. A single iceberg can be acoustically active for years or decades. Multiply this by the thousands of icebergs drifting in the Southern Ocean at any given time. Add the sounds produced by the ice shelf itself, and the acoustic complexity becomes staggering. It is this complexity that makes the attribution of unidentified sounds to ice-related processes both attractive and potentially misleading. Ice can, in principle, produce almost any kind of sound. It can boom, it can whistle, it can groan, it can shriek. When an unidentified sound is detected and its estimated origin is in or near the Southern Ocean, the temptation to attribute it to ice is strong, because ice is capable of producing such a wide range of acoustic signatures. But the very breadth of that capability is also a reason for caution. If ice can produce almost any sound, then attributing any given unidentified sound to ice becomes almost unfalsifiable. It becomes an explanation so flexible it can absorb any data point, and in doing so, it risks losing its explanatory power. A hypothesis that explains everything explains nothing. There is also the matter of sound propagation itself. The ocean is not a uniform body of water. It contains layers of different temperature, salinity, and density. These layers can bend, reflect, and distort sound waves in complex ways. A sound produced near the ocean floor may be refracted upward by temperature gradients, enter the SOFAR channel, travel thousands of kilometers, and arrive at a hydrophone with its spectral characteristics significantly altered. The sound as recorded may not be an accurate representation of the sound as it was produced. It is the sound filtered through thousands of kilometers of ocean, shaped by every layer and gradient it passed through. This means that some of the features of the unidentified sounds, the features that make them so difficult to match to known sources, may be artifacts of propagation rather than characteristics of the source itself. Untangling the effects of long-range propagation from the intrinsic properties of the source is a formidable computational challenge, one that researchers continue to work on but have not fully solved. But here's what makes this truly terrifying. It is not the individual sounds that are most unsettling, It is not any single entry in the catalogue. It is the pattern. It is the sheer number of unidentified signals. It is the frequency with which they appear. It is the vast distances over which they are detected. It is the fact that they have been appearing consistently for more than 30 years. From the earliest NOAA recordings through the present day, the deep ocean is not occasionally producing an unexplained sound. It is routinely, regularly, persistently producing sounds that we cannot identify. The acoustic landscape of the deep sea is populated with voices we do not recognize, signals we cannot attribute, calls and roars and whistles and clicks that have no confirmed source. What we are dealing with is not a handful of anomalies in an otherwise well-understood acoustic environment. We are dealing with an environment that is not well understood. The anomalies are not the exception. They are a feature of our relationship with the deep ocean, a relationship defined by the fact that we can detect but cannot explain, can record but cannot identify, can listen but cannot comprehend. The instruments are functioning perfectly, the recordings are clear, the spectrograms are vivid, and the sounds remain unknown. The most disturbing implication is not that something unknown is out there. It is that something unknown has been out there the entire time we have been listening, producing sounds every day, every year, decade after decade, and we still do not know what it is. The abyss does not keep its secrets out of malice. It keeps them because it is large, and we are small. It keeps them because it is deep, and we can barely reach its surface layers. It keeps them because it has been speaking since long before we existed, and it has no reason to simplify its language for our benefit. And this is where the answer becomes deeply unsettling. The history of humanity's attempt to understand the deep ocean is a history of ambition meeting limitation, of brilliant engineering pressed against an environment that seems almost designed to resist investigation. Every expedition that has descended into the abyss has returned with answers, yes, but also with deeper questions. Every instrument lowered into the deep has revealed not just what is there, but how much we still do not know. The sounds from the abyss are one thread in this larger tapestry, and to understand the attempts to explain them, we must first understand the broader context of what humans have tried and failed to do in the deepest parts of the planet. The first serious attempt to reach the deepest point in the ocean took place on the 23rd of January, 1960. Swiss engineer Jacques Piccard and United States Navy Lieutenant Don Walsh descended to the floor of the Challenger Deep in the Mariana Trench aboard the Bathyscaphe Trieste. The vessel was not a submarine in the conventional sense. It was a freediving craft, a massive hull filled with aviation gasoline for buoyancy, suspended beneath which hung a small steel sphere designed to hold 2 human beings. The descent took nearly 5 hours. During those hours, Piccard and Walsh sat in near total silence inside a sphere roughly 2 meters in diameter, watching the depth gauge creep downward as the water around them turned from blue to grey to utter black. The only sounds were the creaking of the hull under increasing pressure and the quiet hum of their instruments. The pressure at the bottom was immense, equivalent to roughly 8 tons pressing on every square inch of the vessel's hull. When they reached the bottom at a depth of approximately 10,916 meters, they peered through the viewport into complete darkness. What they saw, illuminated by their external lights, was a flat, featureless expanse of pale sediment, a landscape that looked more like the surface of another world than the floor of an ocean. Their stay was brief, roughly 20 minutes, during which the window of the observation gondola cracked under the pressure. They reported seeing a flatfish on the bottom, though this observation was later disputed by some marine biologists who questioned whether a vertebrate could survive at such depth and pressure. Some suggested that what Piccard and Walsh observed may have been a sea cucumber or some other benthic organism whose flat shape resembled a fish in the limited visibility. The Trieste dive was a triumph of engineering and courage, but it also demonstrated the fundamental difficulty of deep ocean exploration. The descent took hours. The time on the bottom was measured in minutes. The observations were limited to what could be seen through a small cracked window in a circle of artificial light surrounded by absolute darkness. No acoustic recordings were made. no sustained scientific observations were possible, and it would be more than 50 years before another human being returned to that depth. That return came in 2012, when filmmaker James Cameron piloted the Deep-Sea Challenger to the bottom of the Challenger Deep, becoming only the third person in history to reach the deepest point on Earth. His vehicle was a radical departure from the Trieste. It was a vertical, torpedo-shaped submersible designed for a single occupant, engineered with syntactic foam buoyancy, and equipped with high-definition cameras, robotic sampling arms, and LED lighting systems. Cameron spent approximately 3 hours on the bottom, collecting sediment samples and recording video footage. His images revealed a world of fine, pale ooze stretching in every direction, disturbed only by the occasional track of a benthic organism or the faint impression of something that had passed through the sediment and left no other trace. Cameron later described the experience as profoundly lonely and desolate, saying the bottom of the Mariana Trench felt like arriving on another planet where life existed only in the most tenuous, ghostly forms. Cameron's expedition advanced our understanding of the Hadal environment. His footage and samples contributed to studies of microbial life at extreme depth and pressure. But his expedition also reinforced how little time humans can spend at these depths and how narrow the window of observation remains. 3 hours on the bottom of an ocean that covers more than 360 million square kilometers. 3 hours in one spot, in one trench, on a planet where the deep ocean floor extends for hundreds of millions of square kilometers of unexplored terrain. In 2019, explorer Victor Vescovo completed a series of dives to the deepest points in all 5 of the world's oceans as part of the 5 Deeps expedition. His submersible, the limiting factor, was the first full ocean depth vehicle rated for repeated dives, and it reached the bottom of the Mariana Trench, the Puerto Rico Trench, the South Sandwich Trench, the Java Trench, and the Molloy Deep in the Arctic Ocean. These dives expanded our knowledge of Hadal environments across multiple ocean basins and revealed that life exists at the deepest points in every ocean, not just the Pacific. Vescovo's team recorded biological activity at depths previously assumed to be essentially lifeless. But even this ambitious program, which represented years of engineering development and millions of dollars in investment, amounted to a handful of brief visits to a handful of points in an incomprehensibly vast space. Each dive lasted a few hours, each covered a tiny patch of seafloor. The deep ocean remained, after all of it, overwhelmingly unseen. And these expeditions, as extraordinary as they were, reached the bottom. The sounds from the abyss do not originate exclusively from the bottom. They come from every depth. They come from the mid-water column, where massive layers of organisms rise and fall with the daily cycle of light and darkness. They come from the vicinity of seamounts, underwater mountains that rise thousands of meters from the abyssal plain but never break the surface. They come from the flanks of mid-ocean ridges, where tectonic plates pull apart and new seafloor is born in eruptions of magma. They come from beneath the Antarctic ice shelf, where glacial ice grinds against rock in perpetual slow motion. They come from volcanic regions thousands of kilometers from any trench. Understanding the sounds requires not just reaching the bottom, but listening everywhere in between. And this is where the story of deep ocean acoustics becomes a story of technology, its capabilities, and its limits. The hydrophone is the fundamental instrument of underwater acoustic research. In its simplest form, a hydrophone is an underwater microphone, a device that converts pressure variations in water into electrical signals that can be recorded and analyzed. The operating principle is straightforward. Sound waves traveling through water create alternating patterns of compression and rarefaction, areas of slightly higher and slightly lower pressure. A hydrophone contains a piezoelectric element, a material that generates a small electrical voltage when it is mechanically stressed. As the pressure waves of a passing sound squeeze and release the piezoelectric element, it produces an electrical signal that mirrors the pressure variations. This signal is amplified, digitized, and stored, creating a recording of the sound. Modern hydrophones are extraordinarily sensitive. They can detect sounds across a wide range of frequencies, from the ultra-low frequency rumbles of geological events, sounds with wavelengths measured in kilometers and frequencies below 1 hertz, to the high-frequency clicks of dolphins and sperm whales, sounds with frequencies of tens of thousands of hertz. The dynamic range of these instruments is enormous. They can record the faintest biological murmur and the loudest volcanic explosion without distortion, provided they are properly calibrated and deployed. When arranged in arrays, multiple hydrophones separated by known distances, they can be used to triangulate the direction and approximate location of a sound source through a process called cross-correlation. By measuring the tiny differences in the arrival time of a sound at each hydrophone in the array, analysts can determine which direction the sound came from and, with enough stations, pinpoint its origin to within a few kilometers or even less. The SOSUS network, as described earlier, was the first large-scale deployment of hydrophone arrays for sustained ocean listening. Its military origins meant that the data was initially classified, but by the 1990s, the scientific community had gained access. What researchers found in the SOSUS data was overwhelming. The ocean was far noisier and far more acoustically complex than anyone had anticipated. The data contained the expected sounds, whale calls, ship traffic, seismic activity, but it also contained things that fit none of the existing categories. Patterns that appeared on spectrograms as vivid, structured signatures, clearly not noise, clearly not equipment artifacts, but equally clearly not matching any known source. NOAA's autonomous hydrophone program expanded on SOSUS by deploying independent listening stations in locations selected for scientific rather than military purposes. These stations were designed to operate unattended for long periods, anchored to the ocean floor, and recording continuously onto internal storage media. Periodically, research vessels would visit each station, retrieve the data, service the equipment, and redeploy the hydrophones. The data was then brought back to laboratories and processed using spectrogram analysis, a method that visualizes sound as a graph of frequency versus time, with the intensity of the sound represented by color or brightness. On a spectrogram, a whale call appears as a distinctive curved line sweeping through specific frequencies. A ship propeller appears as a broad smudge of noise across many frequencies. An earthquake appears as a sudden burst of low-frequency energy that fades over time, and the unidentified sounds appear as patterns that do not match any of these templates, shapes and sweeps, and pulses that resist categorization. The spectrograms were vivid, the sounds were undeniable, but the explanations were elusive, and this led to a series of investigative approaches, each of which advanced the understanding of deep ocean acoustics, and each of which ultimately encountered its own set of limitations. The first major approach to explaining the unidentified sounds relied on what might be called the known source hypothesis. This was the most conservative framework. Researchers assumed that the sounds were produced by known sources behaving in unusual ways, or by known sources in unexpected locations, or by known sources recorded under conditions that altered their acoustic signature in transit. A sound that bore some resemblance to an ice-related event was attributed to ice. A sound that vaguely resembled a biological call was tentatively attributed to biology. A sound detected in a region of known volcanic activity was attributed to volcanism. This approach had the advantage of parsimony, of not requiring the existence of anything new, anything undiscovered, anything that would challenge existing models. But it had the significant disadvantage of often resting on weak evidence. The attribution of the Bloop to ice calving, for example, became widely accepted over time, but the attribution of the Upsweep to volcanic activity remains tentative decades later, supported by geographical plausibility but not by direct observation. The train has never been convincingly linked to a specific geological feature, and dozens of smaller, unnamed transient signals in the archive resist even tentative attribution under this framework. The known source hypothesis works best when the unknown sound closely resembles a known sound that has been recorded under controlled conditions. It struggles when the match is imperfect, when the unknown sound shares some features with a known category, but deviates in ways that could be significant. or could be artifacts of distance and distortion. The ambiguity is often irresolvable without additional data that would require visiting the source, a step that is usually impractical for sounds originating in the deep ocean. A second approach focused on biological possibilities. And it is here that the investigation took on a particularly fascinating and frustrating character. The ocean is home to an estimated 2.2 million species, of which fewer than 250,000 have been formally described. The deep ocean, in particular, is thought to harbour a vast number of undiscovered species. Could some of the unidentified sounds be the calls of unknown animals? This hypothesis is not unreasonable. It is, in fact, well supported by precedent. New species of marine life are discovered regularly, and some of these discoveries have been startling in their scale and implications. In 2018 alone, researchers described more than 1,500 new marine species. Some of these discoveries included organisms of considerable size, not just microscopic creatures or tiny invertebrates, but substantial animals living at depths where they had never been observed before. The history of marine biology contains numerous examples of large animals that were unknown to science until relatively recently. The megamouth shark, a filter-feeding species that can reach lengths of more than 5 meters, was not discovered until 1976. The colossal squid, which can grow to lengths exceeding 12 meters, was not directly observed alive in its deep-sea habitat until the early 2000s. New species of beaked whales, animals that can exceed 7 meters in length, have been described as recently as the 21st century. If animals this large can escape detection for so long, it is not unreasonable to ask what else might be down there. But the biological hypothesis encounters several formidable challenges. The most significant is the question of amplitude. Many of the unidentified sounds are extraordinarily loud. The bloop, before its ice attribution, was estimated to be louder than a blue whale call. The upsweep is detectable across the entire Pacific basin, a feat that requires an extraordinary amount of acoustic energy. The slowdown was recorded by sensors spanning thousands of kilometers. These levels of acoustic output require enormous energy that must be generated by the sound-producing apparatus of whatever is making the noise. In the biological world, the loudest sounds are produced by the largest animals. This is not a coincidence. It is a consequence of physics. Sound production requires the vibration of a structure, a membrane, a set of vocal cords, a swim bladder, and the power of the sound is related to the size and mass of that vibrating structure. A larger structure can displace more water, creating more powerful pressure waves. The blue whale, the largest animal known to have ever lived on this planet, produces the loudest biological sounds ever recorded, calls that can exceed 188 decibels. For an unknown biological source to produce the kinds of sounds captured in the NOAA recordings, it would likely need to be extremely large, far larger than any known marine species. The math is striking. Consider the relationship between body size and call intensity across known marine species. Dolphins, weighing perhaps 200 to 300 kilograms, produce clicks that reach roughly 230 decibels in water, but these are extremely brief pulses focused in a narrow beam. Sperm whales, weighing up to 50 tons, produce clicks of up to 236 decibels, the loudest sound produced by any living animal, but again in short, directional bursts. Blue whales, weighing up to 150 tons, produce sustained low-frequency calls of up to 188 decibels. The unidentified sounds in question would, if biological, require a source producing sustained signals at intensities comparable to or exceeding those of blue whales, from a location deep in the ocean in a frequency range that does not match any known whale species. An organism producing sound at the power levels of the upsweep would need a body mass and a sound-producing apparatus unlike anything in the biological record. This does not make the hypothesis impossible, but it makes it extraordinarily difficult to defend without evidence. And it gets stranger, because the frequency characteristics of the unidentified sounds often do not match what we would expect from a biological source. Biological sounds tend to have certain spectral properties. They tend to be produced in patterns that serve communicative or navigational functions, repeated calls, rhythmic clicks, songs with identifiable structure. Some of the unidentified sounds do exhibit pattern-like features, but others are singular events, brief eruptions of acoustic energy that occur once and never repeat. A biological source would in most cases produce sounds repeatedly as part of its ongoing behavior. A sound that occurs once at enormous power and then never appears again is difficult to attribute to an animal, unless that animal is so rare that its vocalizations are almost never captured, or unless the sound is produced only under extremely unusual circumstances. The numbers are striking in another way as well. If we consider the total area of ocean monitored by existing hydrophone arrays and compare it to the total area of the deep ocean, the fraction that is covered is vanishingly small. The autonomous hydrophone stations operated by NOAA in the equatorial Pacific, for example, cover a strip of ocean a few thousand kilometers long. The Pacific Ocean alone covers more than 160 million square kilometers. The monitored area represents a tiny sliver of the total. This means that for every unidentified sound that is detected, there may be many more that occur in unmonitored regions and are never recorded at all. The catalogue of unexplained sounds is not a comprehensive inventory. It is a sample drawn from a tiny fraction of the ocean, and there is no way to know how representative that sample is. But here's the problem. The biological hypothesis, while not impossible, lacks the one thing that would make it compelling: evidence. No unknown large marine animal has ever been observed that could account for the unidentified sounds. No carcass has washed ashore with vocal apparatus consistent with the acoustic signatures in question. No sighting, no photograph, no tissue sample, no DNA evidence. Nothing beyond the sounds themselves suggests the existence of an unknown biological source of such magnitude. The hypothesis remains a possibility, but it is a possibility that floats unsupported, sustained by the absence of a better explanation rather than by the presence of positive evidence. A third line of investigation explored geological and geophysical mechanisms, and this approach has arguably produced the most progress, though progress is a relative term in a field defined by how much remains unknown. The ocean floor is not a static surface. It is a dynamic, active geological environment, driven by the same tectonic forces that build mountains and trigger earthquakes on land. Along the mid-ocean ridges, new seafloor is constantly being formed through volcanic activity. These ridges are not narrow lines. They are broad, mountainous systems, sometimes hundreds of kilometers wide, with rift valleys, volcanic peaks, and complex fault systems. The geological activity along these ridges is continuous. Earthquakes occur daily. Volcanic eruptions, both explosive and effusive, take place beneath thousands of meters of water, many of them never observed by any instrument. Hydrothermal vents are widespread along these ridges. These are openings in the ocean floor where superheated water, rich in dissolved minerals and gases, erupts into the cold, deep ocean. The water emerging from these vents can reach temperatures of more than 350 degrees Celsius, though the extreme pressure at depth prevents it from boiling. When this superheated, mineral-laden fluid meets the near-freezing ambient seawater, it creates dramatic chemical reactions. Minerals precipitate out of solution, forming towering chimney-like structures called black smokers and white smokers. The fluid dynamics at these sites are complex, involving turbulent mixing, convection cells, and the continuous interaction of hot and cold water masses. These processes can produce sound. Gas bubbles rising through narrow channels in the rock produce acoustic emissions. Water flashing to steam inside fractures and cavities produces sharp cracking sounds. The sudden collapse of newly formed rock structures, undermined by the flow of superheated water, can generate loud, impulsive signals. The resonance of volcanic chambers, partly filled with magma and gas, can produce low-frequency tones that persist for minutes or hours. And the tectonic stresses along the ridges, the constant pushing and pulling of plates, generate a background of seismic noise that includes tremors, grinding sounds, and the occasional sharp report of a fault slipping. Researchers have attempted to characterize some of these sounds directly. In the 1990s and 2000s, a series of expeditions deployed hydrophones near known hydrothermal vent fields along the Juan de Fuca Ridge in the northeastern Pacific and the mid-Atlantic Ridge. These close-range recordings captured a range of acoustic emissions, including the low rumble of fluid flowing through rock, the sharp cracking of thermal stress fractures, and the higher-pitched hissing of gas and steam escaping through narrow apertures. Some of these recordings bore a faint resemblance to certain features of the unidentified sounds detected at long range, but the resemblance was always partial. The close-range recordings captured sounds as they were produced, without the distortions introduced by thousands of kilometers of propagation. The long-range recordings captured those same categories of sounds, if that is what they were, after they had been transformed by their passage through the ocean. Comparing the two was like trying to identify a song you have heard clearly by listening to a version that has been played through a wall, down a corridor, and across a stadium. The general character might be recognizable, but the specific details that would allow a confident match are lost. There have also been attempts to use seismological data to correlate unidentified acoustic events with known geological events. If an unidentified sound was produced by an earthquake or a volcanic eruption, then the seismological record should show a corresponding event at or near the estimated source location at the time the sound was detected. In some cases, such correlations have been found, strengthening the geological hypothesis for those particular sounds. But in other cases, no corresponding seismological event can be identified. The sound exists in the acoustic record without any counterpart in the seismological record, which either means the source was not a conventional earthquake or eruption, or it means the seismological network, which has its own gaps in coverage, simply missed it. The absence of a seismological correlation is not proof that the source was not geological. It is simply another gap in the data, another absence where presence would be needed to resolve the question. But here is the persistent difficulty. While these geological mechanisms can certainly produce sound, and while some of the unidentified acoustic signals are plausibly consistent with geological origins, matching a specific unknown signal to a specific geological process requires direct observation. A hydrophone can record a sound from 3,000 kilometers away with extraordinary fidelity. It can tell you the frequency, the duration, the amplitude, the direction. What it cannot tell you is whether that sound was produced by a collapsing lava tube on a mid-ocean ridge, a fracturing ice shelf in the Southern Ocean, a whale species no one has ever encountered, or some entirely novel process that has no name in any textbook. The attribution requires either observing the source directly, by deploying instruments or vehicles at the source location, or by demonstrating a precise match between the unknown sound and a sound that has been recorded under known controlled conditions. Both of these requirements are extraordinarily difficult to meet in the deep ocean. The distances are vast, the depths are extreme, the costs are prohibitive, and so the sounds accumulate in the record, and the explanations remain provisional. A fourth avenue of investigation concerns what might be called compound sources, situations where multiple acoustic phenomena interact to produce a signal that does not match any individual source. This concept is not exotic. It is a natural consequence of the ocean being a complex, three-dimensional acoustic environment. Consider a scenario in which the grinding of ice against rock produces a low-frequency drone. Simultaneously, that drone passes over a submarine canyon whose geometry happens to amplify certain frequencies and suppress others, reshaping the spectral character of the sound. The signal then enters the SOFAR channel and travels thousands of kilometers, during which further distortion occurs as the sound interacts with layers of different temperature and salinity. By the time the sound arrives at a distant hydrophone, its spectral signature may bear little resemblance to the original ice grinding event. It has been filtered, amplified, distorted, and reshaped by the environment through which it has passed. The resulting recording might not match the known signature of ice grinding, or canyon resonance, or any other single process. It would appear as a new, unidentified sound, born from the interaction of multiple known processes, but unrecognizable as any one of them. This kind of compound source, could explain some of the more puzzling unidentified signals, particularly those whose spectral characteristics seem to straddle the boundary between biological and geological categories. But the compound source hypothesis is extremely difficult to test. Reproducing the interaction of geological, hydrological, and environmental factors at the scales and pressures of the deep ocean is beyond our current experimental capability. We would need to identify the source location, understand the local geology and oceanography in detail, model the acoustic propagation path from source to receiver, and then demonstrate that the combination of these factors produces a signal matching the recording. This level of analysis has been attempted for only a handful of sounds, and even then, the results are rarely conclusive. Then there is the question of the Antarctic ice sheet, which has emerged as a major suspect in many of the unidentified sound cases, and which deserves examination in its own right. Antarctica is surrounded by a vast shelf of ice that extends out over the Southern Ocean, in some places reaching hundreds of kilometers from the coast. This ice shelf is in constant motion, fed by glaciers flowing down from the interior of the continent and losing mass through calving, melting, and ablation at its edges. The dynamics of this ice are staggering in scale. Individual icebergs calving from the shelf can be the size of small nations. Iceberg B-15, which calved from the Ross Ice Shelf in 2000, was approximately 295 kilometers long and roughly 37 kilometers wide. It was larger than the island of Jamaica. As such an iceberg drifts with the ocean currents, it produces a continuous symphony of acoustic events. Low-frequency booms when internal stresses cause it to crack, high-pitched squeals when it scrapes against the seafloor or against other ice, sustained rumbles when it rolls or overturns, broadband crashes when pieces calve from its edges. A single iceberg can be acoustically active for years or decades, producing thousands of individual sound events over its lifetime. Multiply this by the thousands of icebergs drifting in the Southern Ocean at any given time. Add the sounds produced by the ice shelf itself as it flexes and fractures under tidal forces and wind stress, and the acoustic complexity becomes overwhelming. The Antarctic ice system is, in acoustic terms, one of the loudest and most varied natural sound sources on the planet. The Antarctic ice hypothesis is attractive in part because it offers a single explanation for multiple unidentified sounds. The bloop, the slowdown, Julia, and possibly the train have all been tentatively linked to ice-related processes in the Southern Ocean. The estimated source locations of several of these sounds fall within or near the region of Antarctic ice activity. The spectral characteristics, when analysed with ice-specific models, show degrees of consistency with known ice sounds. The case is not definitive, but it is plausible. But the attractiveness of the hypothesis is also a reason for caution. When a single explanation is stretched to cover many different phenomena, there is a risk of over-attribution, of forcing diverse data into a single framework, simply because it is convenient, and because ice, as an acoustic source, is so extraordinarily versatile. Ice can produce almost any kind of sound. It can boom, it can whistle, it can groan, it can shriek, it can rumble, it can click. This versatility means that almost any unidentified sound can be plausibly attributed to ice if the analyst is willing to accept a sufficiently loose match. But a hypothesis that can explain everything risks explaining nothing because its predictive power approaches zero. If ice can make any sound, then saying a particular unidentified sound is probably, ice does not actually tell us very much. Not every unknown sound is necessarily an icequake. The deep ocean is a complex environment with many potential sources of sound, and an over-reliance on any single explanation can obscure the true diversity of what is happening beneath the waves. Consider the case of the so-called bioduck, a case that offers both hope and a cautionary tale. The bioduck was a repetitive, pulsing sound detected in the Southern Ocean for decades. It was named for its vaguely duck-like quality when played at normal speed, a rhythmic series of pulses that repeated with metronomic regularity. For years, the bioduck was a genuine mystery. Its source was unknown. Its regularity suggested a biological origin, the kind of rhythmic, repetitive call that animals use for communication or echolocation, but no species could be identified as the producer. Researchers proposed various candidates: fish, invertebrates, even mechanical sources. None of the proposals could be confirmed. Then, in 2014, a team of researchers managed to attach acoustic recording tags directly to Antarctic minke whales. These tags, small devices attached to the whale's skin with suction cups, recorded the sounds produced by the whales as they went about their daily lives. When the recordings were analysed, they matched the bioduct's signal precisely. The frequency, the duration, the pulse pattern, the repetition rate, every feature of the bioduct corresponded to sounds produced by Antarctic minke whales. A sound that had puzzled scientists for more than 50 years was finally attributed to a known species of whale. The mystery was solved, not by speculating from a distance, not by running acoustic models, not by proposing hypotheses based on plausibility, but by getting close enough to the source to observe it directly. This case is instructive in several ways. It demonstrates that patient, methodical research can eventually resolve even long-standing acoustic mysteries. It shows that the answer can sometimes be surprisingly ordinary, not a new species or a new geological process, but a known animal whose sounds had simply never been recorded at close range. It also reveals something important about the limitations of remote acoustic analysis. For 50 years, researchers had speculated about the bioduct. They had proposed hypotheses, run acoustic models, compared the sound to every known source in the database. None of these efforts produced the answer. The answer came only when someone physically attached a recording device to the animal responsible. All the spectral analysis, all the modeling, all the hypothesis testing from a distance was ultimately insufficient. The resolution required proximity. It required being there. This is perhaps the most sobering lesson of the bioduct case. Remote analysis can narrow the possibilities. It can rule out certain categories of source. It can provide clues and constraints. But for sounds produced in the deep ocean, remote analysis alone may never be sufficient to achieve conclusive identification. The only reliable path to identification is direct observation of the source, and direct observation in the deep ocean is one of the most difficult and expensive things that human beings can attempt to do. The deep ocean resists investigation not through any active defense, but through the simple, implacable facts of its physical nature. The pressure is lethal, the darkness is absolute, the distances are continental, the costs are measured in millions. Every instrument that descends must be engineered to survive conditions that would destroy ordinary equipment. Every vehicle that dives must carry its own light, its own power, its own atmosphere. Every expedition must be planned months or years in advance, staffed by specialists, supported by research vessels, and funded by agencies whose budgets are always under pressure from competing priorities. The result is that the deep ocean receives a tiny fraction of the investigative attention that is lavished on more accessible environments. More scientific papers are published each year about terrestrial insects than about the entirety of the deep ocean, but it also illustrates the staggering time scales and technical requirements involved. It took more than 50 years to identify the source of the bioduct. It required the development of miniaturized acoustic tagging technology that did not exist when the sound was first recorded. And the bioduct was a sound produced relatively near the surface, by an animal that, while difficult to approach, was at least accessible. The minke whale lives in waters that research vessels can reach. It surfaces to breathe. It can be observed, approached, and tagged. The unidentified sounds from the deepest parts of the ocean present a much greater challenge. The sources may be at depths of 5, 6, or 10 kilometers. They may be geological features that cannot be tagged or followed. They may be organisms too deep, too large, too dispersed, or too rare to encounter. They may be processes that occur only intermittently, producing sound for a few minutes, every few decades. The gap between detection and identification may be measured not in decades but in centuries. The bioduct resolution is a hopeful precedent, but it is also a reminder of how far we have to go. There is one more line of inquiry worth examining in detail, and it concerns not the sources of the sounds, but the medium through which they travel. The ocean is not a uniform body of water. It is stratified, layered, internally complex. It contains thermoclines, layers where temperature changes sharply with depth. It contains haloclines, layers where salinity shifts. It contains pycnoclines, layers where density gradients affect the movement of water and the propagation of sound. These layers are not static. They shift with the seasons, with the weather, with the tides, with the massive circulation patterns that move water from the equator to the poles and back. Sound passing through this layered medium does not travel in straight lines. It bends. The physics governing this bending is described by Snell's law, the same principle that explains the bending of light as it passes from air into water. A sound wave traveling from a region of lower sound speed into a region of higher sound speed will bend away from the boundary. A wave moving in the opposite direction will bend toward it. In the ocean, where sound speed varies continuously, with depth, temperature, and salinity, the effect is that sound waves follow curved paths, arcing upward and downward as they travel through the water column. The consequences of this bending are far-reaching. A sound produced at a particular depth may follow multiple paths to a distant receiver. One path may arc upward, reflect off the surface, and return downward. Another may arc downward, reflect off the seafloor, and return upward. A third may travel through the SOFAR channel, bouncing between the upper and lower boundaries of the channel without ever touching the surface or the bottom. Each of these paths has a different length, and each traverses different water conditions. The result is that the same sound can arrive at a single hydrophone multiple times, each arrival slightly different in timing, amplitude, and spectral character. This phenomenon, known as multipath propagation, creates a complex pattern of arrivals that can make a simple brief source sound appear as a prolonged complex signal. A single crack of ice might arrive as a cascade of overlapping pulses. A single volcanic explosion might arrive as a drawn-out rumble. The relationship between the recorded signal and the original event is mediated by the entire ocean between them, and that mediation can be profound. A sound produced near the ocean floor may be refracted upward by temperature gradients, enter the SOFAR channel, travel thousands of kilometers, and arrive at a hydrophone with its spectral characteristics significantly altered. The sound as recorded may not be an accurate representation of the sound as it was produced. Certain frequencies may have been enhanced by the constructive interference of multiple reflected paths. Others may have been attenuated by absorption or destructive interference. The temporal structure of the sound may have been stretched or compressed by variations in propagation speed along different paths. The result is that the recorded signal is a distorted version of the original, shaped by every layer and gradient and boundary it passed through during its journey from source to receiver. What the hydrophone captures is not the original voice of the source. It is that voice after it has been processed by the ocean itself, a processor of immense complexity and one whose parameters we can only partially characterize. This has profound implications for the identification of unknown sounds. If the spectral features that make a sound unidentifiable are artifacts of propagation rather than characteristics of the source, then the sound might actually be a perfectly ordinary event, an ice quake, a volcanic eruption, a whale call, that has been acoustically transformed beyond recognition by its passage through the ocean. Untangling the effects of long-range propagation from the intrinsic properties of the source is a formidable computational challenge, one that requires detailed knowledge of the ocean conditions along the entire propagation path, knowledge that is rarely available. The attempts to explain the sounds from the abyss have been varied, creative, and often compelling. Ice calving, volcanic resonance, unknown biological sources, compound acoustic phenomena, propagation distortion. Each of these explanations has merit. Each accounts for some of the observations, but none of them, singly or in combination, accounts for all of the unidentified signals in the ocean's acoustic record. The catalogue of explained sounds grows slowly, one mystery at a time, each resolution requiring years or decades of effort, and often the development of entirely new technology. The catalogue of unexplained sounds grows faster, fed continuously by the autonomous hydrophones that record day and night, year after year, capturing new signals that add to the archive of the unknown. And the fundamental asymmetry persists. We can listen better than we can understand. We can detect more than we can explain. We can hear the abyss with exquisite precision. We just cannot yet tell what it is saying. And this is where the answer becomes deeply unsettling, because the limitation is not temporary. It is not a problem that will be solved by a single expedition or a single technological breakthrough. It is a structural feature of our relationship with the deep ocean, a relationship defined by the fact that the ocean is the largest, deepest, least accessible, and least understood environment on the planet we call home. The sounds will continue, the recordings will accumulate, and for the foreseeable future, at least some of the whistles, clicks, and roars from the abyss will remain exactly what they are, sounds without a name. There is a number that once heard is difficult to forget. We have explored, by most scientific estimates, roughly 5% of the world's oceans. 5%. That means 95% of the water on this planet. The water that covers the majority of its surface. The water that reaches depths of nearly 11 kilometers. The water that contains the largest habitat on Earth remains essentially unexplored by human beings. Not unmapped in the sense that we do not know it is there. We know the oceans exist. We know their approximate boundaries and depths, but unexplored in the sense that no human eye, no camera, no instrument has ever directly observed what lies within the overwhelming majority of the ocean's volume. We have not been there. We have not looked. We have not listened. The data we possess comes from the margins, from scattered expeditions, from isolated instruments, dangling in an immensity of darkness. Let that sink in. We live on a world dominated by ocean, and we have barely looked at it. We have sent rovers to crawl across the surface of another planet, recording every rock and grain of sand they encounter. We have launched telescopes to peer at galaxies billions of light years away, capturing light that left its source before our solar system existed. We have mapped the human genome, cataloguing 3 billion base pairs with single nucleotide precision. We have built machines that can process trillions of calculations per second. We have split the atom, landed on the moon, and photographed a black hole at the center of a distant galaxy. And yet, beneath the waves of our own planet, there is a darkness so profound and a volume so immense that we have not even begun to survey it in any comprehensive way. The maps that exist of the deep ocean floor are in most places less detailed than maps of the surface of Venus. This is not an exaggeration. The surface of Venus has been mapped using synthetic aperture radar from orbiting spacecraft, producing global maps with resolutions measured in hundreds of meters. The surface of Mars has been mapped to similar or better resolutions. But the ocean floor of our own planet, hidden beneath kilometers of water that blocks electromagnetic radiation, has been mapped primarily using satellite-derived gravity data and ship-based sonar surveys. The satellite gravity data provides a global picture but at very low resolution. The resolution of our best global ocean floor maps derived from this method is approximately 5 kilometers. This means that any object smaller than 5 kilometers across, any seamount, any ridge, any canyon, any volcanic feature less than 5 kilometers in diameter simply does not appear. It is invisible. It is a blank spot on the map of our own world. Ship-based sonar surveys can achieve much higher resolutions, down to a few meters in some cases. But these surveys are slow, expensive, and cover only narrow strips of seafloor directly beneath the ship. A research vessel conducting a multi-beam sonar survey might cover a swath of seafloor roughly 10 to 20 kilometers wide, depending on depth, at a cruising speed of 8 to 12 knots. This means that mapping a single square degree of ocean floor, an area of roughly 12,000 square kilometers at mid-latitudes, can take weeks of continuous surveying. The total area of ocean floor that has been mapped by ship-based sonar at high resolution is estimated at less than 25% of the total. The remaining 75% or more has been mapped only at the coarse resolution provided by satellite gravity measurements, a resolution that would be considered embarrassingly inadequate for any land surface on Earth. To appreciate what this means in practical terms, consider what might be hidden at the resolution gap. A seamount 3 kilometers in diameter, rising 2,000 meters above the abyssal plain, would not appear on a satellite gravity-derived map. An active hydrothermal vent field, typically spanning a few hundred meters at most, would be entirely invisible. A submarine canyon system, potentially tens of kilometers long but only a few kilometers wide, might show as nothing more than a faint smudge or might not appear at all. These are not trivial features. They are precisely the kinds of geological structures that could produce the unidentified sounds in the acoustic record, and they are invisible on the maps we currently possess. The implications of this for the sounds from the abyss are profound and unsettling. If 95% of the ocean is unexplored, then the vast majority of potential sun sources have never been observed. We do not know how many hydrothermal vents exist on the ocean floor. Estimates range from tens of thousands to hundreds of thousands, but the true number is unknown because the majority of the mid-ocean ridge system has never been surveyed at sufficient resolution to detect them. We do not know how many submarine volcanoes are currently active. We do not know how many species of deep-sea organisms produce sound. We do not know how many geological features, seamounts, canyons, fracture zones, transform faults, are capable of generating acoustic signals under the right conditions. We are trying to identify sounds produced by an environment that we have not mapped, generated by processes we have not observed, and possibly made by organisms we have not discovered. This is not science fiction. This is the current state of ocean science, not a failure of effort or intelligence, not a consequence of neglect or indifference, but a reflection of the sheer scale of the task. The ocean contains approximately 1.335 billion cubic kilometers of water. That is a volume so large that it resists intuitive comprehension. The volume of all the land above sea level on Earth is roughly 125 million cubic kilometers. The ocean's volume is more than 10 times that. It is a body of water so vast that it could contain the entirety of the Earth's dry land 10 times over and still have room remaining. The volume of the deep ocean, below 1,000 meters, represents the vast majority of this total, and within that volume, we have directly observed only the tiniest fraction. Every remotely operated vehicle dive, every submersible expedition, every camera tow, every deep water instrument deployment represents a pinprick of light in a vast darkness. Add them all together, every dive ever made, every camera ever lowered, every sample ever collected, and the total area and volume of deep ocean, directly observed by human technology, is a rounding error in the overall total. The number of humans who have been to the deepest point in the ocean can be counted without running out of fingers. As of recent years, the total stands in the low double digits for those who have reached the bottom of Challenger Deep, including the recent dives by Victor Vescovo and a small number of subsequent expeditions. More people have orbited the Earth in spacecraft. More people have stood at the summit of Everest. More people have run a 4-minute mile. The deepest point on our own planet is more exclusive in terms of human visitation than the surface of the moon. Let that sink in. And yet the ocean is not a distant, alien place. It is here. It is beneath the waves off every coastline on Earth. It begins at every beach, every harbour, every river mouth. The deepest trenches are separated from the surface world, not by the vacuum of space, not by the friction of a rocket launch, not by the radiation belts and the cold of interplanetary travel, but by water, the same substance we drink, the same substance that falls as rain, the same substance that makes up roughly 60% of the human body. The abyss is close. It is closer in many cases than the nearest city. The Mariana Trench is closer to the populated islands of the Western Pacific than many towns are to their nearest metropolitan center. The mid-ocean ridge system passes within a few hundred kilometers of inhabited coastlines in several parts of the world. The deep ocean is not out there, somewhere beyond the horizon. It is right there, beneath the ships and the swimmers and the fishing boats, separated from the world of air and light by nothing more than depth, and it is as alien as anywhere in the known cosmos. The conditions at the bottom of the ocean, the absolute darkness, the crushing pressure, the near-freezing temperatures, the complete absence of photosynthesis, the chemistry shaped by hydrothermal input, and the slow rain of organic debris from above, these conditions are as foreign to the human body and to surface life as the conditions on any planet we have yet studied. We could, in principle, survive in a pressurized habitat on Mars more easily than we could survive unprotected at the bottom of the Mariana Trench. The ocean is, in the most literal sense, an alien world embedded within our own. The biological dimension of this ignorance is particularly striking. New species from the deep ocean are discovered with startling regularity. Every major deep-sea expedition returns with specimens that are new to science, organisms that have never been described, never been classified, never been given a name in any language. The rate of discovery has not slowed. If anything, it has accelerated as new technologies have made it possible to reach deeper waters and to sample more effectively. The Census of Marine Life, a decade-long international effort completed in 2010, catalogued more than 250,000 known marine species, and estimated that the total number, including undiscovered species, might be approximately 1 million or more. Subsequent research has revised that estimate upward. In 2023, an international research team conducting surveys of deep-sea environments near the Clarion-Clipperton zone in the Central Pacific reported the discovery of more than 5,000 species previously unknown to science, most of them collected from the abyssal seafloor at depths between 4,000 and 6,000 meters. 5,000 species from a single region, from a single series of surveys conducted over a limited number of years. The organisms included polychaete worms, nematodes, crustaceans, sponges, and a variety of other invertebrates, whose forms and behaviors were unlike anything in the existing literature. Some had body plans that suggested adaptations to conditions we do not yet fully understand. Others belonged to taxonomic groups so poorly known that placing them within existing classification schemes required the creation of entirely new categories. And the Clarion-Clipperton zone is just one area of the deep ocean floor, an area that has received more scientific attention than most because of its potential for deep-sea mining. Vast expanses of the Indian Ocean, the South Atlantic, and the Southern Ocean have received far less attention. The Hadal Trenches, the deepest environments on Earth, have been sampled only sporadically, and each sampling effort has revealed species found nowhere else. The Hadal zones of different trenches appear to harbour distinct biological communities, separated from each other by the relatively shallow water of the abyssal plains that surrounds them, functioning as isolated islands of extreme depth. If this density of undiscovered biodiversity is representative of the deep ocean as a whole, and there is no particular reason to think it is not, then the total number of undescribed deep-sea species may run into the hundreds of thousands, or even the millions. Among these undiscovered species, it is reasonable to assume that some reject sound. Sound production is widespread in the marine world. It is not an exotic adaptation confined to a few specialized groups. It is a fundamental biological capability shared by an astonishing variety of marine organisms. Fish grunt, click, pop and drum, using their swim bladders, their skeletal structures, and specialized muscles. At least 800 species of fish are known to produce sound, and the true number is almost certainly much higher. Shrimp snap their claws with a force that generates sonic shockwaves, creating one of the most pervasive sources of biological noise in the ocean. Whales sing across ocean basins. Dolphins echolocate with rapid-fire clicks that can detect objects the size of a golf ball at distances of more than 100 meters. Sea urchins produce scraping sounds as their spines and teeth move against rock. Lobsters produce rasping sounds by rubbing their antennae against their exoskeletons. Even organisms that do not intentionally produce sound generate noise as a byproduct of their movement, their feeding, their burrowing, their swimming. In the deep ocean, where light is absent and vision is useless for all but the closest encounters, sound is the primary sensory modality. It is how organisms detect predators, find mates, navigate terrain, communicate, and establish territory. The selective pressure to produce and receive sound is, if anything, stronger in the deep ocean than in shallower waters, because there is no alternative sensory channel that can operate over similar distances. Chemical signals disperse slowly in the relatively still deep water. Touch requires direct contact. Electrical fields, used by some shallow water species, attenuate rapidly. Only sound can bridge the vast distances between organisms dispersed across the abyssal plain. If the deep ocean harbors millions of undescribed species, and if even a fraction of those species produce sound, then the acoustic environment of the deep sea contains voices we have literally never heard before, voices that may account for some of the unidentified signals in our recordings. Consider the case of the so-called 52 Hz whale, an example that illustrates how even a single, unusual acoustic source can defy identification for decades. Since 1989, hydrophones have detected a whale call at a frequency of approximately 52 Hz, significantly higher than the calls of any known whale species. Blue whale calls typically range from 10 to 39 Hz. Fin whale calls center around 20 Hz. The 52 Hz call follows migration patterns consistent with a baleen whale, but at a frequency that matches no known species. The animal producing this call has never been visually identified, never photographed, never sampled. It exists, as far as science is concerned, only as a sound, a voice in the darkness with no confirmed body attached to it. Some researchers have speculated that it may be a hybrid between two whale species, or an individual with an unusual vocal anatomy. Others have suggested it may represent an undescribed species. The mystery remains open. And it is a mystery concerning a whale, an air-breathing mammal that must surface regularly and that lives in waters accessible to research vessels. If a whale can produce sounds for decades without being visually identified, what hope do we have of identifying the sources of sounds produced at abyssal depths by organisms that never surface, in waters no research vessel has ever visited? The technological gap is another facet of the deeper truth, and it is a gap that closes slowly despite impressive advances in ocean engineering. Our instruments are improving, but they are still inadequate for the task at hand. The autonomous hydrophone arrays deployed by NOAA and other agencies cover a tiny fraction of the ocean's area. Large stretches of the Atlantic, Indian, and Southern Oceans have no dedicated acoustic monitoring at all. The equatorial Pacific is relatively well covered, thanks to NOAA's long-term program, but even there, the spacing between hydrophones is hundreds or thousands of kilometers. A sound produced in the gap between two stations may be detected at both, but with reduced fidelity and limited directional information. A sound produced far from any station may not be detected at all. There are entire ocean basins where no permanent acoustic monitoring exists. Emerging technologies offer some promise. Underwater gliders, autonomous vehicles that can travel through the ocean for months at a time using minimal power, can carry hydrophones and other sensors into previously unmonitored regions. Cabled ocean observatories, permanent installations connected to shore by fiber optic cables, provide continuous real-time data from specific locations. The Ocean Observatories Initiative, a network of such installations operated by the United States, includes seafloor nodes and moored arrays that provide continuous acoustic data from sites in the Atlantic and Pacific. But even these advanced systems cover only a handful of fixed locations. They are points of light in a vast darkness, and the darkness between them remains unmonitored. Moreover, the instruments themselves have frequency limitations. Most of the NOAA hydrophones are optimized for low-frequency sounds, the kinds of signals produced by earthquakes, whales, and large-scale ice events, sounds with frequencies below roughly 100 Hz. Sounds at higher frequencies, the clicks of dolphins, the snapping of shrimp, the possible calls of smaller deep-sea organisms may fall outside the optimal recording range or be attenuated beyond detection by the distances involved. Higher frequency sounds are absorbed more rapidly by seawater than lower frequency sounds, which means they can only be detected at shorter ranges. This creates a fundamental bias in our acoustic monitoring. The catalogue of unidentified sounds is weighted heavily toward the low-frequency end of the spectrum. There may be entire categories of unidentified mid-frequency and high-frequency signals being produced in the deep ocean that are simply not being captured by the existing instrumentation. We are listening, but we are listening through a filter, and that filter lets through only a fraction of the ocean's acoustic output. Consider, too, the phenomenon known as the deep-sea dawn chorus. In shallow waters, the dawn chorus is well documented, a surge of biological sound production that occurs around dawn as fish and invertebrates become active. In recent years, researchers deploying hydrophones in deep water have detected a similar phenomenon at depths of several hundred to over 1,000 meters, a daily pulse of acoustic activity that coincides with the massive vertical migration of deep-sea organisms. Each night, trillions of small fish, squid, and crustaceans rise from the deep to feed in shallower waters, and each dawn they descend again. This migration, the largest daily movement of biomass on the planet, produces sound. The deep-sea dawn chorus has been detected at multiple locations, and its acoustic characteristics are still being catalogued. Some components of this chorus match known biological sources, others do not. The dawn chorus is a reminder that the deep ocean has daily rhythms of sound production that we are only beginning to document, rhythms that have been repeating for millions of years without any human being ever hearing them. There is also the question of temporal coverage. Autonomous hydrophones record continuously, but they require periodic servicing, data retrieval, and sometimes replacement. During service intervals, recording may be interrupted for days or weeks, and even when the hydrophones are operational, the data they produce is vast, far too vast for manual analysis. A single hydrophone recording continuously at standard sampling rates can produce hundreds of gigabytes of data per year. Multiply that by the number of stations in a network, and the total volume of acoustic data becomes staggering. Researchers typically use automated detection algorithms to scan the recordings for signals above a certain threshold of amplitude or spectral distinctiveness. These algorithms are effective for loud, distinct signals, the kinds of sounds that would later be given names like the Bloop or the Upsweep. But they may miss quieter, subtler sounds, sounds that fall below the detection threshold or that do not match the spectral templates the algorithms are programmed to recognize. The archive of ocean acoustic data is, in effect, a library that no one has time to fully read. There are sounds buried in the data that have never been examined by a human analyst, signals that were recorded years or decades ago, and that sit on hard drives and magnetic tapes, unheard and unanalyzed. Machine learning and artificial intelligence techniques are beginning to be applied to this problem, with algorithms trained to detect and classify acoustic events in large datasets. But these techniques are still in their early stages for deep ocean applications, and they face a fundamental chicken and egg problem. To train an algorithm to recognize a particular type of sound, you need labeled examples of that sound, and for sounds that have never been identified, no labeled examples exist. The possibility that the answer to one or more of the outstanding acoustic mysteries is already sitting in an archive somewhere, recorded but never examined, is not trivial. It is a real and acknowledged limitation of the field. The philosophical implications of this situation are worth pausing to consider. We often speak of the ocean as if it were a single, coherent entity, something we can know and manage and protect. We speak of ocean policy, ocean governance, ocean conservation, as if we were dealing with a system we understand. But the truth is that the ocean is an environment so vast and so deep that our knowledge of it is necessarily fragmentary. We know the surface reasonably well. We have reasonable maps of the continental shelves. We have studied the waters above the sunlit zone in considerable detail. But below that thin upper layer, our knowledge thins rapidly. The abyssal plains, the Hadal trenches, the mid-ocean ridges, the submarine canyons, the deep fracture zones, these places are as foreign to us as the surface of another planet. They are within our reach, in the sense that we can send instruments there, but they are beyond our grasp, in the sense that we cannot sustain a presence there, cannot observe them continuously, cannot build the kind of comprehensive understanding that comes from long-term, direct, repeated engagement with an environment. We have studied the deep ocean the way a person might study a city by standing on its outskirts and listening. We have heard sounds coming from within. We have detected patterns and rhythms. We have noted that some sounds are familiar and others are not. But we have not walked the streets. We have not entered the buildings. We have not met the inhabitants or learned the language. We are listeners at the edge of a world whose interior remains unexplored, and the sounds we hear from that interior are our only connection to whatever is happening within. The sounds from the abyss are a reminder of this gap. They are a reminder that the ocean is not a passive backdrop to human civilization, not a blue expanse we see from aeroplanes and forget about once we land. It is an active, dynamic, acoustically rich environment that operates according to its own rules, generates its own signals, and keeps its own secrets. When we hear a whistle sweeping upward through frequencies we cannot explain, or a roar so powerful it shakes instruments thousands of kilometers away, or a rhythmic pulse that continues for months, and then falls silent without explanation, we are hearing the voice of a world we have barely begun to explore. And the appropriate response is not frustration or fear or dismissal, but a kind of humility. The humility that comes from recognizing the boundaries of one's own knowledge, and the humility that comes from standing at the edge of an immensity and admitting that the immensity is larger than one's ability to comprehend it. Something is wrong with our assumptions about this planet. We assume that because we live on it, we know it. We assume that because we have named the oceans, drawn lines on maps, and built ships to sail across their surfaces, we understand what lies beneath. We assume that the world has been explored, that the age of discovery is over, that the blank spaces on the map have all been filled in, and the unknown has been conquered. These assumptions are wrong. They are not slightly wrong, not wrong at the margins, not wrong in detail, while being right in broad strokes. They are profoundly, fundamentally wrong. The blank spaces have not been filled in. They have merely been covered over with a thin veneer of blue on our maps and globes, concealing an abyss of ignorance that extends from the continental shelves to the Hadal trenches and from one pole to the other. We speak of the age of exploration as if it ended centuries ago, with the mapping of coastlines and the charting of sea routes. But the coastlines and the sea routes are the surface. They are the skin of the ocean, the two-dimensional boundary where water meets air. Below that skin lies a three-dimensional world of staggering volume, and that world has barely been entered, let alone explored. The true age of exploration, the age in which we begin to understand the largest environment on our own planet, has not ended. It has barely begun. The sounds from the abyss are evidence of this. They are dispatches from a frontier that most people do not even realize exists. A frontier that is not on another planet or in another galaxy, but directly beneath the surface of the water that laps at our shores. The sounds coming from that abyss are not signals we can choose to ignore. They are not background noise to be filtered out of cleaner data. They are data, they are evidence. They are fragments of a message from a world we have not yet visited, a world that exists beneath us at every moment, producing acoustic signals that propagate through black water with a persistence and a regularity that borders on the mechanical. And they will continue whether or not we listen, whether or not we understand, whether or not we send the instruments and the vehicles and the funding necessary to turn detection into explanation. The abyss does not wait for us. It has been producing these sounds for far longer than we have been listening, and it will continue to produce them long after the current generation of hydrophones has rusted and failed. The deeper truth is not that the ocean is hiding something from us. The deeper truth is that the ocean is not hiding anything at all. It is making sounds openly, continuously, in every direction, at every depth, without pause and without restraint. The sounds are there for anyone who listens. They have always been there. They were there before we invented the hydrophone. They were there before we invented the ship. They were there before we existed as a species. The deeper truth is that we are simply not capable, not yet, of understanding what we hear. And that gap between hearing and understanding is not merely a technical problem awaiting a solution, not a matter of building a better hydrophone or deploying a faster computer. It is a condition of being a species that has been listening to the deep ocean for barely 70 years on a planet whose oceans have been producing sound for an incomprehensibly longer span of time. 70 years of listening against billions of years of speaking. We are new to this conversation, unimaginably new. The ocean is not. What does it mean to share a planet with an environment we cannot fully perceive? This is not an abstract philosophical question posed for the sake of intellectual exercise. It is a practical one, with consequences that touch policy, industry, science, and the very way we think about our place on this world. The decisions we make about the ocean, how we regulate fishing, how we manage shipping lanes, how we extract minerals from the seafloor, how we respond to climate change, are all made on the basis of incomplete knowledge, and the sounds from the abyss are a vivid, almost poetic illustration of just how incomplete that knowledge is. Consider the question of deep-sea mining. As terrestrial mineral deposits become harder to access and demand for metals essential to modern technology continues to grow, attention has turned to the seafloor. Polymetallic nodules, potato-sized lumps of manganese, nickel, cobalt and copper, litter vast areas of the abyssal plain. Cobalt-rich crusts coat the slopes of seamounts. Massive sulfide deposits form around hydrothermal vents, rich in copper, zinc, gold and silver. These deposits represent potentially enormous mineral wealth, and the technology to extract them is being actively developed. Several nations and private companies have obtained exploration licenses for deep-sea mining in areas governed by the International Seabed Authority. Pilot mining operations have been proposed, and in some cases tested. These deposits are found at depths of 3,000 to 6,000 meters, in the very environments from which the unidentified sounds emanate. Proposals to mine these deposits involve dragging heavy collector vehicles across the abyssal plain, crushing nodules and rock, and pumping sediment-laden water back into the water column through riser pipes. The mechanical noise generated by these operations would be substantial, a continuous industrial drone introduced into an environment that has known only natural sounds for its entire existence. The sediment plumes could spread for hundreds of kilometers, smothering benthic organisms and altering the acoustic properties of the water column. The physical disturbance of the seafloor would destroy habitats that take thousands or millions of years to form. The acoustic impact of such operations has barely been studied. We know that the deep ocean is an acoustic environment of extraordinary sensitivity. We know that organisms at these depths rely on sound for survival, for finding food, for avoiding predators, for locating mates. We know that the existing noise floor is shaped by natural processes that have been operating for geological ages, and we are proposing to introduce industrial noise into this environment without knowing what is already there, without knowing how the existing acoustic ecosystem functions, without knowing what might be disrupted or destroyed. There is a kind of recklessness in this, not the recklessness of malice, but the recklessness of ignorance. We cannot protect what we do not understand, because we cannot predict the consequences of our actions. If the sounds from the abyss include the calls of organisms that are essential to deep-sea ecosystems, organisms that serve as food sources, as nutrient recyclers, as links in ecological chains we have not yet described, and if industrial noise disrupts those calls, we may cause damage that we cannot measure, cannot perceive, and cannot reverse. Even without mining, the ocean is already becoming noisier. Global shipping traffic has increased the ambient noise level of the ocean by a factor of roughly 10 over the past half-century. The low-frequency hum of cargo ships, tankers, and container vessels now pervades every ocean basin, creating a background of anthropogenic noise that masks biological signals and may be altering the behavior of marine species, from whales to fish to invertebrates. Sonar systems used by naval vessels and commercial survey operations produce intense pulses of sound that can travel hundreds of kilometers. Seismic airgun surveys, used to prospect for oil and gas deposits beneath the seafloor, produce some of the loudest sounds in the ocean, repeated blasts of low-frequency energy that can be detected across entire ocean basins. Each of these sources adds to the noise floor, raising the threshold below which natural sounds cannot be heard. The unidentified sounds from the abyss exist against this increasingly noisy backdrop, and as the background rises, the quieter among them may be lost entirely. The precautionary principle, the idea that in the absence of knowledge we should err on the side of caution, has never been more relevant than in the context of the deep ocean. We are reaching into a world we do not understand and proposing to reshape it for our own purposes, on our own timeline, according to our own needs. The sounds we cannot explain are a warning that the world we are reaching into is far more complex, far more active, and far more acoustically alive than our plans account for. Climate change adds another layer of urgency. The ocean absorbs a vast proportion of the excess heat being trapped in the atmosphere by greenhouse gases, roughly 90% of the additional thermal energy accumulated in the Earth's climate system. As the ocean warms, its acoustic properties change in ways that have cascading effects on everything that lives in it and everything that produces sound within it. Warmer water transmits sound faster, which means the depth of the SOFAR channel shifts. A shift in the SOFAR channel changes the paths along which sound travels, which changes the distances over which sounds can be detected, which changes the acoustic landscape experienced by every organism in the ocean. Species that have relied on the acoustic properties of the ocean remaining stable over their lifetimes and over many generations now face an environment in which those properties are changing at a rate unprecedented in any period for which we have data. Alongside warming, the ocean is becoming more acidic as it absorbs increasing amounts of carbon dioxide from the atmosphere. This acidification has an acoustic consequence that is less widely known but potentially significant. Sound absorption in seawater is partly dependent on the concentration of dissolved borate and carbonate ions, which in turn depends on the pH of the water. As the pH drops, the absorption of low-frequency sound decreases. This means that in a more acidic ocean, low-frequency sounds travel farther before they fade. The acoustic horizon of the ocean is expanding. Sounds that once would have been absorbed before reaching a distant hydrophone may now arrive with detectable intensity. This could mean that some of the sounds appearing in modern recordings are not new events but old ones, events that have always been occurring, but whose acoustic signatures were previously absorbed before they could be detected. The changing chemistry of the ocean is in effect turning up the volume on the deep. The patterns of biological sound production are also changing as species migrate to cooler waters or alter their behavior in response to temperature stress. The sounds of ice in the Southern Ocean are changing as Antarctic ice shelves thin and fracture at accelerating rates. More calving means more ice quakes. More ice quakes means more acoustic energy in the water. The baseline of ocean noise is shifting, and it is shifting in ways that make it harder to distinguish signal from background, harder to identify new sounds against a changing noise floor, harder to establish what is normal when normal itself is in flux. The acoustic environment of the deep ocean is not a fixed, stable system. It is a system in flux, shaped by forces that are themselves changing, and we are trying to understand that system at the very moment it is being transformed. The sounds we record today may not be the same sounds we would have recorded 50 years ago. They may not be the same sounds that will be produced 50 years from now. The acoustic record of the deep ocean is not a static archive. It is a living document continuously rewritten by the forces that shape the ocean itself. The sounds from the abyss also carry a philosophical weight that extends beyond science and policy. They remind us that the world is larger than our experience of it. They remind us that the planet we inhabit contains depths we cannot visit, pressures we cannot endure, and darkness we cannot penetrate. In an age when it sometimes seems as though every corner of the world has been photographed, catalogued, uploaded, and commented upon, the deep ocean remains genuinely unknown. It is a frontier in the truest sense of the word, a place where the next discovery could change our understanding of biology, geology, or acoustics in ways we cannot predict. There is something both humbling and exhilarating about this. Humbling because it reminds us that our species, for all its technological prowess, is still a newcomer to this planet. We have been building advanced civilizations for perhaps 10,000 years. The ocean has been here for an incomparably longer span. We have been listening to its depths for roughly 7 decades. It has been speaking for ages beyond our measurement. In that context, our ignorance is not a failure. It is simply a consequence of scale. The ocean is too large, too deep, and too old for us to know in a single lifetime, or a single century, or perhaps ever. The sounds from the abyss are a measure of that scale, a measure of the distance between what we know and what there is to know. And exhilarating, because it means the story is not over. The unidentified sounds are not dead ends. They are open questions, invitations to investigate, to build better instruments, to launch new expeditions, to listen more carefully and more broadly, and with greater patience than we have managed so far. Every unexplained signal is a thread that, if followed, could lead to a discovery of profound significance, a new species, a new geological process, a new understanding of how sound propagates through the deep ocean, a new insight into the relationship between ice, water, rock, and life at pressures and temperatures that exist nowhere else. The sounds from the abyss are not frustrations, they are promises, they are evidence that there is still something left to find. We stand at the shore, looking out over water we cannot see through, water that extends to depths we can barely reach, water that carries sounds we cannot explain, and we have a choice. We can treat those sounds as noise, as a static, as background, to be filtered out and forgotten, or we can treat them as what they are, messages from a part of our own planet that we have not yet met, messages written in a language we do not yet speak, transmitted through a medium we do not yet fully understand, produced by sources we have not yet identified, and carrying implications we have not yet grasped. The choice seems clear, but it requires investment, it requires patience, it requires the recognition that understanding the deep ocean is not a luxury, not an academic exercise, not a curiosity to be pursued when more pressing matters have been resolved. It is a necessity for science, a necessity for policy, a necessity for the simple fundamental act of knowing where we live. The ocean floor is not a destination we have passed. It is not a chapter we have closed and moved beyond. It is a destination we have barely approached. The sounds rising from it are not echoes of something past. They are signals of something present, something ongoing, something that asks to be understood. And the fact that we have heard them at all, that our instruments have captured even a fragment of the ocean's acoustic life, is itself a kind of wonder. Not long ago, the deep ocean was as silent to us as the far side of the moon. Now it speaks, however imperfectly, through the data on our spectrograms and the recordings in our archives. That it speaks at all should be enough to make us listen harder. The ocean does not know we are listening. It does not care. It does not adjust its sounds for our benefit. It does not simplify its signals so that we might understand. It does not pause for our instruments or repeat itself for our recorders. It simply does what it has done for an incomprehensibly long time. It groans, it whistles, it clicks, it roars. It produces sounds that travel for thousands of kilometers through water darker and colder and deeper than anything we can comfortably imagine. And it does this without regard for whether anyone is recording, without regard for whether anyone cares, without regard for the small, curious species that recently began lowering microphones into its depths. There is a sound in the deep Pacific that sweeps upward through frequencies no catalogued animal can produce. It has been doing so since at least 1991, rising and falling with the seasons, peaking near the equinoxes, and no one has ever visited its source. There is a sound in the Southern Ocean that lasts for 7 minutes and descends in frequency, as though the planet itself were exhaling a long, slow release of breath from somewhere beneath the ice. There is a sound that pulses like a heartbeat, steady and rhythmic, from a location no expedition has ever reached. There are sounds that appeared once in the record, brief and powerful, and then vanished, never to be heard again. And there are sounds buried in archives on hard drives and magnetic tapes that have never been played back, never been examined by a human analyst, never been given names. The ocean's acoustic record is a library written in a language we are only beginning to decode, and the library grows faster than we can read it. We gave some of these sounds names: the bloop, the upsweep, the slowdown, Julia, the train, the whistle. The names are human impositions on phenomena that have no use for them. Giving them names made them feel more manageable, more contained, as if naming a thing could bring it within our control. It is an old instinct, this urge to name. We name storms, we name constellations, we name the craters on distant moons. Naming gives us the illusion of familiarity, the sense that we have taken the measure of the thing named. But the names are just labels on containers we cannot open. The bloop has been tentatively explained, the others have not, and beyond the named sounds, there are hundreds, perhaps thousands, of unnamed signals sitting in the data, sounds that were too brief, too faint, or too common to attract a name. The named mysteries are the visible surface of a much deeper mystery. The sounds themselves remain what they always were, signals from a world we can hear but cannot see, a world we can detect but cannot fully explain, a world that exists beneath us at every moment, and that carries on its business regardless of our attention or our understanding. The abyss is patient. It does not rush its disclosures. It has been producing sounds for longer than our species has existed, longer than the continents have held their current shapes, longer than the ice caps have waxed and waned through their ancient cycles. It will continue producing them long after the last hydrophone battery dies, long after the last spectrogram has been printed and filed, long after the last researcher has turned off the lights in the last laboratory. The question is not whether the sounds will continue. They will. The question is whether we will continue to listen, whether we will invest the resources, build the instruments, fund the expeditions, and sustain the patience required to turn a catalogue of mysteries into a catalogue of understanding. There is a particular kind of courage in listening to something you cannot explain. It is the courage of admitting that the world exceeds your comprehension. It is the courage of sitting with uncertainty, of resisting the temptation to force a premature answer onto an open question, of allowing the unknown to remain unknown until the evidence is sufficient to resolve it. The scientists who first catalogued the Bloop, the Upsweep, the Slowdown, and the rest showed this courage. They recorded sounds they could not explain, named them, published them, and said, honestly, that they did not know what made them. In a culture that often rewards certainty and punishes doubt, this honesty is itself a kind of achievement. The sounds remain unresolved, not because science has failed, but because science, at its best, refuses to claim knowledge it does not possess. The whistles, clicks, and roars from the abyss are not threats. They are not warnings. They are not calls for help. They are not messages directed at us. They are simply the sounds of a world doing what it does, a world of unimaginable pressure, perpetual darkness, and life so resilient that it thrives where nothing, by any surface reckoning, should be able to survive. They are the sounds of rock splitting along faults that have been active since before anything walked on land. They are the sounds of ice cracking under stresses that build over centuries and release in seconds, shattering the silence of the deep with sudden violence. They are the sounds of water, moving through channels and canyons carved by forces we have barely documented, forces that shape the ocean floor as relentlessly as wind and rain shape the mountains above. They are, perhaps, the sounds of creatures whose bodies and behaviors we have not yet imagined, creatures adapted to a world so different from ours that encountering them would be like encountering life on another planet. And they are, in the end, the sounds of our own ignorance, a gentle, persistent, unhurried reminder that the planet we call home has kept most of its story to itself. The deep ocean does not owe us its secrets. It does not owe us explanations or revelations or the satisfaction of resolved mysteries. It owes us nothing. It was here before us, vast and dark and loud with its own concerns. It will be here after us, unchanged in any way that matters. It is the largest single feature of this planet, and it operates on timescales and at pressures and in darkness that make our brief span of attention seem like the flicker of a candle in a cathedral. What we have learned about it in our 70-odd years of serious listening amounts to a whisper caught through a closing door. The door is not locked, it is not barred, it is simply heavy, and the room beyond it is very, very large. Listen, not with your ears, but with the understanding that comes from knowing how little we know. Listen to the silence between the sounds, the vast stretches of unmonitored ocean where signals rise and fall and are heard by no one. Listen to the idea that beneath every wave, beneath every ship, beneath every whale and every fish and every grain of sinking sediment, there is a darkness that contains something we have not yet found, something that makes sounds we cannot yet explain, something that exists in the largest, deepest, most unexplored space on this planet, a space that begins just a few meters below the surface of every ocean and extends downward for kilometers into a world of crushing weight and absolute night. We will go back. We will lower more instruments. We will build better hydrophones, more sensitive receivers, more powerful processors. We will send more vehicles into the deep, more cameras into the dark, more microphones into the silence that is not silent. And slowly, sound by sound, mystery by mystery, we will begin to decode the language of the abyss. It will take decades. It will take centuries. It may take longer than we can imagine. But the sounds will wait. They have always waited. They were there before we arrived, and they will be there when we are ready. The abyss is not empty. It has never been empty. It is full of sound, full of pressure, full of life, full of mystery. It is full of whistles that rise through the water column and travel across hemispheres without losing their shape. It is full of clicks that pulse in patterns we cannot decode, rhythms that may carry meaning we are not equipped to recognize. It is full of roars that shake instruments anchored to the seafloor thousands of kilometers from their source, vibrations that speak of forces beyond our experience, and it will remain so, speaking its quiet, thunderous language into the black water, day after day, year after year, century after century, with a constancy that mocks our fleeting attention, until we learn at last to understand what it has been saying all along. The ocean is the oldest voice on this planet, the most patient, and we have only just begun to hear it.